Yeah. Hi, I'm here in case the chair of the session wants to.
Yeah, hello.
Hi.
Yeah, hi. I'm Arijit.
Hi, I'm Mandar.
Yeah.
So I think it works fine.
Yeah.
I don't really think there's an issue.
No, it looks fine.
Okay. All right. So we can start in about, I guess, a few minutes.
Yeah. In 5 minutes we can start.
Are you able to see the screen okay? Arijit?
Yeah, we can see it, yes.
The full screen, right?
Yeah, I can see the full screen. Yes.
Okay. All right. Yeah, we're set. Arijit, the time allotted is how much? Can you please clarify for me? So it's 30 minutes.
Sure. It's 25 minutes and 5 minutes for discussion.
Okay, good.
Yeah. So I will give you a notification after, let's say, 22 minutes.
Sure.
Yeah. So I think we can start. So,
Yeah, so
good morning, everyone.
maybe I'll just, yeah, so good morning, everyone. Welcome to the first session of this, the morning session of this last day of this international conference on the topology in condensed matter systems. So this session has two speakers, and the chairperson is Professor Iit Saha from IOP Bhubaneswar. So I'll just clarify one thing, that the chairperson has to request the speakers, asking him his or her permission, whether the video can be uploaded in the YouTube after the talk. So if the speaker does not want, then we can remove from the YouTube.
Okay.
Then you can start, Professor Iit Saha.
Okay. Thank you, and good morning, and welcome in the morning session of the topology in the international conference in topology in condensed matter systems. And in the morning session, our first speaker is Professor Mandar Deshmukh from TIFR, and he is going to talk about electric field drives Chern transitions and layer polarization changes in Hofstadter bands of twisted double bilayer graphene. So Mandar, now the stage is yours.
Okay, thank you very much, Professor Saha. I thank you very much for the opportunity to speak about our work. There was some communication error about my talk on Monday. So I'm happy to be here finally and talk about our work. So let me get started. So I'm going to tell you about experiments on twisted systems, a particular creature in the twisted world, which is twisted double bilayer graphene. I will try to explain these terms to you as I go along. But one of the main messages is that in twisted systems with few layers in there, there's an interesting role of polarization. And we show in this work that it's connected to the Chern transitions. And the implication is that what we are showing is a kind of a magnetoelectric coupling arising in the case of Hofstadter bands of the system. Okay, so I gratefully acknowledge the funding that we get from Department of Atomic Energy and Department of Science and Technology that makes this work possible. And let me start off by acknowledging the collaborators in this work who really make this work possible. I get the opportunity to speak about it, but to be sure, these are the people who actually made the work possible. So the work that I will talk about specifically today is led by my student Pratap Chandra Adak, and there's a long-standing collaboration between him and another student, Subhajit, working on different aspects of twisted double bilayer graphene, and Varma and Surya are other people from my lab who have contributed. So we have greatly benefited from the collaboration with Arijit Kundu's extended group at IIT Kanpur and Herb Fertig at Indiana, and the people who did made the actually calculations possible, as Dibya, who's now at Indiana, and Debasmita, she's a PhD student with Arijit and has done a really remarkable job in setting up these very difficult calculations. There are very few people in the world who can actually do these calculations, Hofstadter calculation in twisted systems. So I want to make a point to acknowledge them. And then we have an extended collaboration from in the past where we have learned a lot of different things, collaboration with Jail Jung's group and Bhima and Rajdeep and Amit Agarwal's group at Kanpur, which looks at different physics related to the system, but that has nevertheless helped us understand this system. The experimental system is possible because of very high quality hexagonal boron nitride that we get from Dr. Taneguchi and Watanabe. So having acknowledged my collaborators, let me give you a brief outline of my talk. So I'm going to talk briefly about few layer and twisted systems. They are in vogue and a lot of people are studying them. I will provide information which is sort of necessary to understand the physics that I'll talk about. I'll talk about this twisted double bilayer graphene. What is it? Why is it interesting? Why is it an interesting topological system? And the take-home message is that it has non-trivial valley churn numbers, and it's tunable with electric field. Then I'll get a little bit into Hofstadter bands that arise in this twisted systems, and I will end with trying to give you a sense for the underlying physics of layer polarization and magnetoelectric coupling, which is really interesting for us. Okay, let me get started. So twisted systems are of course of a lot of interest in recent past because of the flat bands, and the flat bands have led to discovery of correlated insulators, then superconductivity around these correlated insulators. Exact mechanism of superconductivity is still being sort of debated, but it has led to a lot of renewed interest. And it has brought together another aspect of correlated physics, which is the physics of ferromagnetism in a completely different, it's an orbital ferromagnet. So a lot of interest has been focused on correlations in these flat bands. And our focus, as I will show you, is in looking at aspects of topology in these flat bands. Okay, just to tell you that the twisting of two layers of graphene or many layers essentially creates a superlattice, which essentially modifies the bands. I will talk more about it, but what this sort of cool animation is showing is creation of a new length scale in the system. So how do these flat bands arise? If you have one Brillouin zone and bands which disperse like that of graphene, then if you put another layer on top, there is a rotation in the K space, and that actually leads to formation of kind of a mini Brillouin zone because of the superlattice structure. And what happens is that if you look at these two sort of K points, which of the two layers which are twisted, when there is no hopping between the two layers, these two K points are kind of unhybridized. But when there is hopping, there's hybridization, and you get some gaps opening up, and you get these flat sort of regions which are flattish, which are flat bands. This is really the genesis of the flat bands in pretty much all Moiré systems. When the tunneling, interlayer tunneling, becomes comparable to tunneling between Moiré, you get these exceptionally flat bands, and that's the starting point of interesting experiments. Okay, now this idea of flat bands in twisted bilayer graphene started it, but it has led to a lot of interesting exploration in other systems. So the system of that I will be focusing on today is twisted double bilayer graphene, which is pieces of two layers of bilayer graphene rotated relative to each other. So instead of using monolayer block, we use a bilayer as a building block to build this twisted structure. So you might say, okay, why do this? What's the benefit? And that my goal is to convince you that it has interesting topological properties, which actually twisted bilayer doesn't have. Okay, on top of it, it has some other features which make it very attractive system. The biggest attractive feature is that electric field, which is applied perpendicular to the plane, tunes the band structure continuously, and also the valley churn numbers, which is really a kind of not seen in very many other systems. So why bilayer as a static building block? Because bilayer has a tunable band structure. So if you just take pristine two layers of graphene, no twisting allowed, it's just Bernal stacked, then in the absence of a perpendicular field, which is basically, you can think of it as the inversion symmetry is preserved, in this bilayer system, you get a gapless system. But when you apply a perpendicular electric field in this direction, you actually break inversion symmetry and you open up a gap. And so it becomes a semiconductor where the gap is actually proportional to some function of the electric field. So this twisted double bilayer has led to a lot of interesting new ideas and new exploration, and we have studied this for last couple of years. So our focus is to look at topological physics and not just the correlated physics. So I will my work today that I'll describe will focus on the topology part. Okay, so now I want to tell you upfront that this system people have kind of studied for a while, and if you calculate the band structure, and I'll show you again a little bit later. But what you see here are some extended bands. Again, you'll see them in more detail, but then a region of flat bands. And as you apply an electric field, so this energy is an interlayer potential. As you apply an electric field, you open up a gap, and you basically, starting from one overlap flat band, you get two flat bands. And this numbers in black are basically the valley churn numbers. So you don't break the time reversal symmetry, so you don't have a net churn number yet, but you have valley churn numbers. And there's an interesting cousin from this family, which is kind of 180 degrees rotated, which is called ABBA. It has pretty much the same band structure, but a totally different churn numbers, valley churn numbers so that's another knob which has actually been little explored. And this is something that we are looking at and I'm going to be talking about today. Okay, so as I said, twisted bilayer graphene doesn't have this kind of rich topological structure. Let me quickly describe the devices. I won't go too much into detail. So we make these twisted structure with an angle we dial in, which rotation. The devices that I will talk about are close to 1.2 degrees. And they look something like this in an optical microscope image, and it has many experimental knobs, gate voltages. So it has two gates, bottom and top gate, and you need two gates basically in a device to independently control charge density and electric field. If you just have one gate, you cannot independently control. And these systems, the pure electric field is a very important experimental knob. Charge density is like Fermi energy. Okay, so electric field actually tunes the band structure. Charge density tunes the Fermi energy. That's how you want to think about it. And how the density and electric field is connected to these knobs is written here. They're kind of a rotation in the space of these two voltages. Okay, the other knobs that are there for us to play with is temperature and magnetic field, and we use them quite a bit. Today's talk will not feature the use of these magnetic field, certainly not temperature, but I'll allude to it. So when you measure 4-probe resistance of these devices, typically at low temperatures, so we measure in a range of temperatures starting from 1.4 Kelvin, 300 millikelvin, and down to sometimes at dilution fridge temperatures. So if you tune the density, you will see peaks in resistance at 0 perpendicular electric field. And as you tune the electric field to some non-zero value, you'll see a peak in resistance. So these peaks in resistance are associated with some gaps. Okay, and these gaps can be quantified and measured, and we have done that in our earlier work. I won't talk about it, but if you have questions, please ask me. Okay, so when you do lots of these measurements, it makes sense to visualize the large data sets using a color scale. So you can think of the number of resistance in the density electric field parameter space, and you can visualize it as a color. Okay, so these are resistance peaks, and red is low resistance region. There are some other features like this cross thing, which I will not talk about. So now how do I understand this electrical transport and the band structure? So actually, my student Pratap, whose slides I have borrowed, has made some excellent slides, which and it should become very clear. So if I look at this point, which is zero electric field, my system looks like this. The gray are extended bands, okay, and these are gaps in the spectrum. So at this point, this is what the system looks like. As I increase the electric field, the flat band splits into two, but it's still gapped up from the remote bands. Okay, and this is the gap that you're beginning to see between the two flat bands. And as you increase the electric field further, you move these electric flat bands, and even they will merge with remote bands. Eventually, both the fragments of the initial flat band will merge with the remote band, and there won't be any flat band available. These are the Moire gaps, which are sort of characteristic of these systems. So this is sort of what it looks like in terms of the slices. Okay. Now, in the past, as I said, we have done detailed work with Rajdeep at TFR, and the calculations are model dependent, but they capture the essence of the experimental results quite well, and we have compared it. Now, one of the interesting things that we have explored that will lead me into today's work is that these gaps of these flat bands have, high Berry curvature, and they can be probed, and we have done that in transport experiments. So the Berry curvature has a very interesting structure in these flat bands. And this was a collaboration with Bhima and Jail Jung's group. And one can probe it. And the way to probe this Berry curvature structure is using the anomalous velocity because of the Berry curvature to sense it. So you get a Valley Hall effect and an inverse Valley Hall effect, which allows you to actually non-locally measure this Berry curvature structure. And in time reversal symmetry protected systems, you can see the Valley Hall effect certainly very nicely. And this is the geometry in which we have done experiments. So these systems have rich Berry curvature, or rather Berry physics. And there are more details in this paper that and I won't talk more about it. So this leads me to sort of the main part of my talk, which is physics related to the topology of these systems. So, the Hofstadter physics, which is sort of the essence of our work, is formed because of sort of two competing length scales coming together. So you have the periodicity due to the ideas given by Bloch. And then another kind of physics that's happening is if you apply a perpendicular magnetic field, you get these cyclotron orbits. And when you combine these two together, you get a very intriguing regime where there is a competition of length scales, which is length scale of the periodicity of the lattice and the magnetic length of the system. And when these length scales sort of have some ratios, you get kind of new emergent bands from the system. These are the Hofstadter bands. And Pratap, my student, had a very nice way to illustrate this using sort of a spirograph, which is something that you might have played with, or kids who have played with it. It's somewhat analogous in spirit. So when you have some ratio of these two length scales, sort of coprime integers p and q, in this limit, you start with Landau levels, and as you sort of travel along, you get these rich structure. These are the Hofstadter sort of bands, and these Hofstadter bands lead to very interesting physics. So Hofstadter did these calculations, but there are ways to understand this physics, a few years down the line, using Vanir diagrams, which basically allow you to look at the gaps in the spectra and make connection to their topological properties. So if you plot these and sort of look at the Vanir diagram, you'll get these Diophantine equations, and this slope gives you the Chern number. And that's a way to probe the Chern number in these in any system, and that's sort of what we'll be using. The technical challenge is that getting to a regime where this ratio of these phi by phi naught, which is sort of like having the two length scales of magnetic length and the lattice length being equal, is hard, and that's why these systems were hard to experimentally realize. But Moiré systems allow precisely experimental realization of using lab scale magnets, cryostats, to get to a regime where a field like 12 or 13, 14 Tesla, an appropriately twisted device can get you. And so the people started with graphene on HBN, and that's the starting point. So the Chern number will basically tell you what's happening at the boundary modes of the system. Now, I showed you a plot like this before. As you apply a magnetic field, something quite interesting starts to happen. This is a zero magnetic field. When you apply a magnetic field, this you can think of it as a kind of a reflection of the spectra, becomes more complex. So this is at something like perpendicular magnetic field of 9 Tesla. So you get this formation of Landau levels, and you get kind of structure, discrete structure, which I will talk more about. I will use terms like this is the electron side. This is called the hole side of this flat band system. Okay, so focus on these flat bands. There's some structure which is there, which I will talk about. These are the Moiré bands that I've already mentioned, Moiré gaps that I've already mentioned. And this is the region that we will focus for the remaining part of the talk. So you see features, you have nu and electric field. As a function of electric field and filling, you see these discrete steps by which the sigma XX changes, indicates gap in the spectrum. Now, how do I understand these? So I can mark out these sort of regions in the electric field and nu direction. But I can also do another experiment, which is on the same device, which is to vary the magnetic field. And remember, I told you when I talked about the Streda formula, you can actually, the Diophantine equation allows you to extract the Chern number of the feature. So if you follow the lines here, they allow you to extract the Chern number and that's what we do. To identify the Chern number of these features, we look at this magnetic field and nu plot to extract out the Chern number. You'll also see that on this axis, this is phi by phi naught. You'll see a modulation, which is the indication of some physics related to the Brown-Zach oscillation. Okay, so let's get started. So if I draw lines corresponding to these gaps in the spectrum, I can draw these kind of lines, and from the Diophantine equation, I can assign Chern number. So this allows me to identify the Chern number of this orange dot, which is this line, and this purple line by calculating the slope from the experimental data. So it tells me the first number is the Chern number. If I go to a different position in electric field, I do the same experiment and I can find out the Chern number. So what I do is I do many such experiments. Well, I don't really do anything. My students do it. You can extract out the Chern number for each of these features. Okay, by doing lots of experiments, and you can assign the Chern number for each of these features. So what we are seeing is as you tune the electric field, you sit at the same magnetic field. You're basically changing the Chern number one at a time. So you start from Chern number of 2, you become Chern number of 1, then you reduce it even further. Okay, 0, then Chern number of -1. Similar things happen for this gap as well. So it's like the Chern number of the gap changes. The way to think about this is, if you have field states and you have a gap, what's really happening is that as a function of electric field, you're peeling away layers of the kind of subset of the Hofstadter band away and merging it out. So each of the gap, whatever the Chern number, actually changes discretely by one at a time. Okay, and sort of these incredibly challenging calculations that Debasmita and Divya did together with Herb and Arijit actually explain these structure very well. So you can calculate the Hofstadter spectrum. This axis V is actually the electric field. And from the calculation, you can also calculate exactly the same axis. So this is the calculated electric field as a function of nu, and you see precisely these discrete switching or changes in the Chern number of the gap. Okay. Now, what underlying physics, which is very interesting, is that using theory, when you probe the polarization of these bands, like the bands here, as a function of electric field.
Mandar,
yeah.
You have 5 minutes.
Okay, yeah, I should be done. As you change the electric field, you will basically have this non-monotonic evolution of energy. A band goes like this, even in experiments. And while that's happening, it's basically a change in the polarization of the bands at different points. So if this is sort of the cartoon which indicates the layer polarization here, then as you go along with electric field, the layer polarization kind of sloshes back between between the layers. Okay, so using experiments and theory, we can connect. So the Chern number is actually related to the magnetization of the state, the orbital magnetization. So there is a direct proportionality between the magnetization of a Chern state and there's a proportionality constant is connected by the gap. But if the system is gapped, you're basically changing the magnetization, and the bands, the layer are reflecting the change in the layer polarization. So this is also something that we calculated. And you can see that as a function of electric field, x-axis is electric field, which is the interlayer potential, you can see changes in the polarization for the Chern gaps. Now, one of the interesting things about these systems, the twisted systems, is that if you have an interesting topology, then the bands can be connected across a Moiré gap of the system, and that's, we see hints of it, and which is also supported by our theory calculations, that if we calculate the spectra and experimentally measure this fan diagram as a function of perpendicular magnetic field at a precise electric field, you see that this Hofstadter gap actually propagates across this Moiré gap. So this is basically the Moiré nu equals 4 is the Moiré gap, because there is fourfold degeneracy of these bands, 2 because of electron and spin, and this gap propagates across it, which is a signature that even across a Moiré gap, the systems are kind of in some sense intertwined, and that is the non-trivial topology being reflected in the experimental data. All right, so I'm done. Let me briefly summarize the experiment. So what we see are in twisted double bilayer Hofstadter physics. Because of the twisting, it leads to another length scale of periodicity. And we see gaps, and these gaps are Chern gaps with non-trivial Chern number, which can be tuned with electric field. Here you see a cascade of steps one at a time as a function of electric field. Okay. And I showed you results from the layer polarization calculations, which show that the layer polarization is changing while these Chern transitions are happening. But the main sort of take-home message that I want to, which is really exciting for us, is that there are open questions about how magnetoelectric couplings arise in systems. Okay, what we are showing is that Chern number changes, which basically changes in magnetization, orbital magnetization with electric field, which is sort of the definition of magnetoelectric coupling. And this magnet is not any generic magnet; it's an orbital magnet. Okay. And we have further plans to examine this in a little bit more detail. I thank you very much for your kind attention. I'm happy to answer any questions that you might have.
Yeah, thank you, Mandar, for a very interesting talk. So now the session is open for questions. Yeah, so I can see 2 raised hands. So
yeah, I've not been looking at chat boxes or anything, but
yeah, not chat
ask
box.
questions directly. Yeah, please.
Yeah.
Yeah. Go ahead. Somebody can ask me a question.
The first question I can see raised hand by Tanushree Shah, Professor Tanushree Shah Gupta.
Hi, Mandar.
Yeah, hi. Hi, Tanushree.
Yeah, nice talk. I have just 2 very, probably very simple question. Is in case of the twisted graphene, not the bilayer graphene, the twist angle had a very specific importance. You reported your experimental result for 1.1 degree of twist angle.
Yeah.
Is there anything special about this 1.1 degree?
Okay, yeah, thank you very much for this question. It allows me to elaborate on something which because of time I didn't spend. So remember in twisted bilayer, the band structure is not tunable with electric. So that's why there is this idea of angle controlling the flatness of the bands. Okay, so that's where the origin of this magic angle idea. Twisted bilayer and many other systems, including transition metal dichalconide based systems, they get around this idea because the bands are tunable with electric field. There's no precise magic angle. There is a range of angles over which the bands are very flat. The flatness extent changes as a function of angle. So these experiments are at 1.2. These are at the cusp of correlations being developing. So if I apply some in-plane magnetic field, I can open up gaps at ns by 2. Okay, so here. So in twisted double bilayer and other systems as well, there is a range of electric fields where you can further engineer the bands, whereas in twisted bilayer, you only have angle knob. Electric field is actually not a knob. So that's why I didn't use terminology like magic angles. This is very close. So people give sort of flat bands from something like 1.1 degrees all the way up to 1.4. And you see kind of correlated states at ns by 2 gaps at something close to 1.3. So this is very close. We want to look at physics of topology, which is without inducing correlations, if you like.
Yeah. So the it's a related question that what is the origin of this non-zero Berry curvature? There is it's a carbon atom. There is no great in-orbit coupling. Is it the twisting that gives rise to some chiral interaction? Of course, you mentioned of orbital magnetism.
Yeah.
But,
so the magnetism in these twisted structures that arises is orbital magnetism because of these edge modes that are circulating. So let me first address your question about the origin of the Berry curvature. So the origin of the Berry curvature is there, even in bilayer, simple bilayer, no twisting of graphene, you have Berry curvature because you have a gap at kk prime points in bilayer graphene, and the Berry curvature is actually tunable by electric field because then you basically tune the gap and the Berry curvature gets modified. It's essentially the same physics coming in. There are gaps and these precise points host the hotspot of the Berry curvature. Okay. So you don't really need any spin orbit or anything. You just need bands which have small gaps, and they can be sources of Berry curvature.
I see.
Okay.
Okay, thank you.
Sure.
Yeah, another quick question. I can see a raise hand from Sudipta Chatterjee.
Yes, sir. So thank you, sir, for a very nice talk. I have a very small query. So you have shown that when you are applying a certain electric field, nearly about minus 0.3 volt, there is the opening up a gap, maybe in slide number 9. So
Yeah.
my query is that what will happen if I increase the intensity of the electric field? And another thing is that, is there any kind of change with applying positive volt instead of the negative voltage at the
Yeah.
gate?
Okay, thanks for this question. Let me just elaborate a little bit on this aspect. So this electric field is 0.3 volt per nanometer, which is actually a quite substantial electric field, even in other devices, forget about twisted. So there is a fair bit of symmetry in positive and negative electric field. So you see this gap closes at 0.3, it also closes at minus 0.3. So there are some asymmetry features, but overall there is a symmetry with electric field, and that's zeroth order that's expected. Okay. Now, as I increase the electric field, which is what I interpret as when you said intensity of electric field, you basically you have this gap, which is high resistance state. If you sit at this point in the device, in the parameter space, as you apply a perpendicular electric field, you actually close this gap. Okay. Fermi energy is the same. So because I hold the Fermi energy precisely at this point. Okay, so the Fermi energy doesn't change, but the gap closes. So it's basically direct evidence that the band structure is getting tuned with electric field. Okay. Does that answer your question?
Yes, yes. Thank you.
Okay. Yeah.
Yeah.
This one.
So one last question, I think, given the time constant. Priya, can you ask the question?
Yeah, can you hear me?
Yeah.
Yeah, Nanda, nice talk. Just a follow-up question on the previous one. So naively, how do you maintain your electric field? And I mean, like, because you have an electric field which induces your carriers. So naively, how does one think of this? That you have a simultaneous electric field which is omnipresent, and you have another electric field which is for gating.
Yeah, so I mean, electrostatics, it's basically electrostatic, simple sort of electrostatics of the device. Okay, so I have two gate. When I apply a perpendicular, when I control these two, and these have some capacitances associated with it, I can induce charge carriers using a linear combination of these two. Okay. Now, if I change the sign of it, you will see that both of these together change the density of charge carriers, but if there's an asymmetric combination of the two gate voltages in using the capacitance, that only controls the electric field, pure electric field change without changing the density or the Fermi energy. Okay. If you just think of a two parallel plate capacitors sharing one common plate in between, and if you write down the equations for the density and electric field, you'll be able to essentially get to this. So this is displacement field, which is kind of proportional to the electric field because of all complications of screening and inside the system. Direct measure of the electric field is somewhat non-trivial. When I use the term electric field, it's basically the displacement field.
Okay.
Yeah, so this is not unique to this. I mean, if you have if you have two gates in any system, even simple bilayer, you can independently control electric field and density.
Okay, thank you.
Sure.
And Manda, last question is that, do you have permission for the organizer to upload your
yeah, sure,
talk?
no problem. No problem. Yeah.
Okay. I think
so
let us thank Mandar once again for the very interesting
I'm happy
talk.
to be here. Thank you very much.
Yeah, so we can go to the next speaker. So our next speaker is B.R. Nanda from Iit Madras. Yeah.
Can I share my screen?
No, Ranjit, you have to share your screen.
Yeah. Is it visible, Arjit?
Yeah. Now it's visible.
Okay, so
Yeah, you can make it full screen. And...
yeah, just give me a second. Is the full screen visible?
Not still not. Yeah, it's not visible. Can you do again this slideshow and check?
Is it visible?
It might help to share the whole screen rather than the application. Sometimes
Yeah.
I see,
has
I
issues. Share the whole screen and then.
I see. It is showing the share. It is not giving the option. Maybe just give me a second.
Sure.
So you have to click on the PowerPoint. Share.
Yeah.
PowerPoint and then click on share.
Yeah, I did that. Share. Okay, is it still visible?
Yeah, your screen is visible.
Not the PowerPoint.
Not the PowerPoint.
So how to share that?
Open
If I
PowerPoint and then we can share. Open that PPT.
no, if I open it, maybe this will work. I think now it should work, right?
Yes.
Yeah. No, it's fine. Okay.
Okay, so let me start by thanking the organizers for giving me this opportunity to deliver this talk at this wonderful forum. I am Ranjit Nanda, faculty in physics at Iit Madras. Today I'm going to give a talk on the non-trivial band topology of perovskites. It's a slightly off-topic material as far as the topology is concerned. This work is carried out by my PhD student Ravi, Mayank, and Amit. And I must acknowledge the funding agencies, that is DST, Ministry of Education, and Iit Madras. Okay, so when I say it's perovskites, I will talk about halides and oxide perovskites as well. We know halides in the sense of, in the context that they are pretty much applicable in the area of photovoltaics, LED, and stuff. There are many articles that have been written. Just a couple of them I demonstrate here, including one of ours. Similarly, oxides specific to transfer metal oxides, these are quite well known, extensively studied in the context of strongly correlated electron physics. Here is a snapshot of few of the information that we see. For example, you see the recent work, Junger predicted how in the low temperature phase you can see a varieties of magnetic phases, and of course change in the transport phenomena with change in the d electrons. Not only the pristine elements, of course, by doping and making heterostructures, one can demonstrate exotic quantum phases in the system. However, this neither the photovoltaics phenomena nor the correlated magnetic phenomena are pretty much the focus of this topic. What attracted my attention is the following: two articles as far as the halides are concerned. Long back, Claudia Felser group came up with the idea that one can indeed create a topological insulator out of barium bismuth oxide. They did the band structure and they saw that there are, let me see the pointer. Yeah, so yeah, this somehow the pointer doesn't work. Okay, follow the arrow. So there are a couple of band inversion points which make the topological invariant Dirac state at the surface when the films are made. Similarly, at the same time, there was a high throughput study in a wide varieties of material by the Stefano Cataldo group. And they predicted that if you look at the halide perovskites, they categorize them into two parts. Some of them are hardly feasible topological materials, and some of them are potentially feasible topological materials. So this became the motivation of our research. And similarly, as far as the oxides are concerned, so there are a lot of works going on iridates. Just one of them I am presenting here, which says that one can indeed create topological states such as nodal ring, nodal points in iridates. Keeping this in mind, I will start my talk. And here in my talk, I'll just give you a perspective of the electronic structure that I obtained using density functional calculation as well as effective Hamiltonian studies. I divided this two family of perovskites, halides and oxide into the non-correlated, correlated regime. In the non-correlated regime is basically the S and P electrons involved in the interaction, where pretty much the chemical bonding and a bit of spin-orbit coupling, if at all is active, decide the electronic structure. And when the system breaks from the centrosymmetric to non-centrosymmetric, then the polarized field alter the band structure. On the other hand, if you look at the correlated system, this is basically defined by the PD electron, PD chemical bonding. On the top of it, there is a strongly correlated interactions, maybe intra-orbital, inter-orbital. And at times there will be competition among the on-site repulsion and the spin orbit coupling, which gives rise to a plethora of topological and magnetic quantum phases. Of course, also if you break the centrosymmetric phenomena, there are possibilities of forming skirmions in this class of materials. On skirmions, there are a large number of talks already delivered in the past 2 days, and I am not touching the discussion on skirmions. My focus will be pretty much on the topological aspects. So let's first go to the non-correlated regime by looking at the perovskites. In fact, the talk is prepared based on the following article that we have published on halides and oxides. So basically, the topological perspectives have been brought from these articles. Let me first focus on the non-correlated regime, purely halide perovskites. And if you look at the experimental articles, these halide perovskites, they exhibit in 3 phases: alpha phase, beta phase, gamma phase. Alpha is the simple cubic phase, beta is the tetragonal phase, and gamma is the orthorhombic phase. And I mean, when you bring to beta and gamma phase, right, you have 2 additional degrees of freedom that alter the electronic structure, that is rotation and tilting, as compared to the alpha phase. However, the broader picture of electronic structure we can simply obtain by looking at the cubic or the alpha phase. The broader picture can be summarized as follows. The interactions are by and large among the B, BP and BS states along with the XP or XS states. Right, they forms a group of bonding lying far below in the energy spectrum, and a group of anti-bonding states lying far above the energy spectrum, and including a set of non-dispersive, not necessarily flat, non-dispersive bands in the middle. Now, depending on the electron count, right? So if the number of electron count is 20, fortunately you ended up having a gap between the bonding S state and bonding anti-bonding S state and anti-bonding P states. That gives the opportunity to create an inversion introducing the spin orbit coupling, and that inversion lead to a invariant Dirac state. The same can be obtained for valence electron less than 20. However, the topological invariant state will no longer lie at the Fermi level, as you can see in the case of barium bismuth oxide. So here you can consider B as the bismuth, X as the oxygen. Now, when we look at the halide perovskites instead of the barium bismuth oxides, for example, CSSN, Cl3, Br3, or IR3, I3, then you see the valence electron count is 20. So when your valence electron count is 20, you are perfectly having a gap in the anti-bonding regime, right? Now, the question is that therefore it becomes a normal insulator. Can I induce a topological insulator out of it? Now, to do that, one needs to apply the external stimuli such as pressure and strain. In this two pieces of work, we focused on both pressure and strain. We show that the moment you compress the system, right, the normal insulator gradually convert a Dirac semi-metal, which I call accidental Dirac semi-metal, which can will be broken with minor distortion and stuff like that. It's not symmetry invariant. Then further compression leads to the band inversion, and that band inversion can give rise to the invariant surface Dirac states. And the same has been demonstrated. The surface states has been demonstrated by K resolved density of states. You see the formation of the invariant Dirac state. Now, not only the pressure, of course, strain can bring the same aspect, that is the normal to topological insulator phase transition. Here I have demonstrated both compressive and tensile. So when you say compressive strain, then and calculate the chain number, you see that the chain number converts from 0 to 1. It's a strong topological insulator, by the way, by nu0, nu1, nu2, nu3, all of them becoming 1. On the tensile side and also further on the comprehensive side, also it becomes Z2 is equal to 0 to Z2 1. It just demonstrates that we have a normal to topological insulator phase transition by simply applying pressure and strain. And pressure and strain are pretty much can be applied at the lab with ease. But the story is not as simple as we thought, because so far we have discussed the alpha phase. Now, if you bring the beta phase into gamma phase, as I told you, there are two additional degrees of freedom that plays the spoil short. That is the rotation, that is which I have defined by theta AB, and the tilting, which I have defined by theta C. This rotation and tilting influences the electronic structure, which we'll explore in next couple of slides. Now let's look at the beta phase or the tetragonal phase. I did a full phase calculation on DFT calculation in the space spanned by strain that I defined by C by A ratio and the rotation del theta B. And we studied a stability curve analysis and also the electronic structure analysis. We obtained that if you compress significantly to bring C by A to 0.85 or so, you can immediately jump from a Ni to Ti state that I'm talking on the left. And similarly, you can apply the opposite side of the strain. You can immediately jump to the Ti state as well. However, the stability curve tells that it is quite unstable to achieve the Ti state when you change the CIA to C by A more than greater than 1. However, tetragonal phase gives the possibility of obtaining a Ti phase. But when we examine the orthorhombic phase, now we have, in addition to theta AB, that is theta C, that is the tilting, right? So then we examined and we saw that there is a total energy analysis and the band gap analysis. We kind of summarize that the orthorhombic phase doesn't show any NITI phase transition. So when we talk about the halide perovskites, probably the alpha phase and the beta phase are the most plausible material for topological phase transitions. How to understand the effect of the rotation and tilting? Here we come up with a very simplistic tight binding model Hamiltonian. If you go back and look at our the molecular orbital picture, obviously the 4 orbital from B and the 9 orbital from X are involved in the interaction. So in principle, one has to create a Hamiltonian with 13 orbital basis. And if you decouple the spin, then it will be 26 orbital bases. Now, furthermore, if you want to move from cubic to tetragonal or rhombic, the unit cell size increases to maintain the translational symmetry, and that in principle creates an orthorhombic phase at least 64 plus 64 basis Hamiltonian, which is difficult to trace and track and study. Therefore, a simplistic approach is required. As we learned that only the anti-bonding states are responsible for the topological phenomena, and by and large, the electron structure are the Fermi. So we kind of created an effective Hamiltonian, including the BB interaction, that is the tin in case of CSSN X3 or CSPBI3 to be PP interaction as well as S interaction. These are the 4 orbitals that has been taken into the picture. Now, what is the benefit of it if you take these 4 bases? And if you need to look at all the alpha, beta, gamma, we have introduced the effective interaction among the B and X through BB, right? And if we ignore the X, then all alpha, beta, gamma, and all 3 phases, the B lattice is more or less same. The B lattice doesn't change except the fact that there will be change in the C by A and C by ratio. So therefore, one can easily convert this 64 plus 64 or 32 plus 32 into a 4 plus 4 effective Hamiltonian. And if it is spin decoupled, then 8 cross 8. And all the rotation and tilting one can map through the tight binding parameter interaction parameter that I defined T and epsilon. These are the interaction parameters. The details can be found from the papers that I have referred. Now, this pretty well match with the bulk band structure of alpha and beta gamma phase, just to validate the model. And then we demonstrated the role of theta and C by A. So you see that as you keep on changing the C by A and keep on changing the theta, right? The band slowly touches, then open up. So when they touches and open up, basically they create a accidental Dirac metal, then convert ensure the band inversion leading to a topological insulating phase. We in principle show that the rotation doesn't have much of a role. Instead, in fact, the rotation and tilting angles create a wider band gap to realize and makes it difficult to realize the topological insulator phase transition. However, C by A, the strain or the pressure, are the one of the most important tunable parameter to realize the topological insulating phase. In fact, we could develop a descriptor model. The descriptor model takes into account the various parameter of C by A, parameter of interactions, like which I have defined in terms of epsilon 1, 1, 1. These are details which we can discuss later if time permits. And then we can expand them using the simple Taylor expansion, saying that how they depend on the C by A. Here del C by A means the variation in the C by A, first order or second order. This can gives a glimpse of the normal to topological insulator phase transition, how it can be tailored. Now, in fact, this also tells that if you develop a surface Hamiltonian using a slab method, wherever you see the topological phase transition in the topological insulating phase band with the band inversion, you can really create an invariant surface Dirac state at the surface. This is just to validate the idea that we have evolved with. Now, so far we have discussed with the centrosymmetric where the inversion symmetry is maintained. So the story is not over yet. What happens when the system becomes non-centrosymmetric? When the system becomes non-centrosymmetric and inversion symmetry breaking field is included, it comes into the picture in the Hamiltonian. And once the inversion symmetry breaking field, it comes into the picture of the Hamiltonian, the resulted eigenstates, and no more Cramer degenerate. They breaks in the momentum space as well as energy space. Now, this part we further examine and studied past the DFT perspective. We found that if you take a non-centrosymmetric compound, halide perovskites, for example, MAPBI3, I know that this story is much more complex than people imagine. There are a lot of controversies regarding whether the MAPBI3 or organic halide perovskites are really centrosymmetric or non-centrosymmetric. There are two sides in the aisle. One side supports being non-centrosymmetric, other side supports it being centrosymmetric. However, they come to the conclusion that at the local area, macroscopically, they may be centrosymmetric. In local periphery, they are non-centrosymmetric. In that context, if we model our calculations, and we found that with compression, indeed, the band inversion occurs, and one indeed reaches to a topological insulating state. However, actually, when in the centrosymmetric, when you try to build pressure, you gradually reach to a Dirac metallic phase, then the topological insulating phase. In this case, that doesn't happen. The band never even closes. So therefore, we examined both from the density function and tight binding perspective, and looked at how the band gap evolved as the with compression. And we say that there is a fast order phase quantum phase transition. As far as the band gap is concerned, it drops at certain point. Immediately, the band inversion occurs without achieving the Dirac metal phase. When the electric field, the inversion symmetric field, which I represented here through gamma, is present, and when the inversion symmetric breaking field is taken away, of course, there is a smooth variation of the band gap, as I can see. So now, can we apply such large pressure? There's a practical difficulties. I think there are some promising aspects. There are a group in Stanford. We examined probably the MAPBI3, I'm sure. Right? They could apply the pressure up to 50 gigapascal and maintain the crystallinity of the system to some extent. And they indeed never reported the band gap dropping down to zero. In the bulk, but the surface analysis, I exactly don't remember, but surface analysis suggests there are glints of metallic state which we can attribute to the formation of the Dirac states. Now, what does Dirac state, the topological state, look like if you switch on this inversion, switch on this non-centrosymmetric behavior, or introduce the polar inversion symmetric breaking field? Now, no longer you have only a single Dirac state, as you saw in the case of centrosymmetric. There are two-fold non-degenerate Dirac node, one lying at the bottom and another lying on the top. And in between, you have a beautiful Dirac circle that we can create in this class of material. So it pretty much resembles with the hexagonal bilayer graphene, where the two Dirac cones interpenetrate and creates a Dirac circle with two nodes, one on the top and one on the bottom. So this pretty much the topological phenomena of halide perovskites. However, in recent days, what has been examined is not only the band formation in the momentum space, also the spin texture, the other quantity that varies in the momentum space, keeping in mind the applications in the area of spintronics, orbitronics, and topotronics. The spin texture that is defined by the Pauli spin expectation of the eigenvectors that we get in our main field or in our study. There are a good number of literature who talks about the spin texture. It's pretty much well known. Raspa spin texture, Dresselhaus spin texture. And when both of them are there, then there are resultant persistent spin textures, which symbolically I represented in 3 of the below diagrams, as I borrowed the picture from a symbol group and also from Professor Dasgupta's group. So the spin variation in the momentum space varies. Interestingly, for the persistent case, there is a sharp divide between the downspin and upspin. We wanted to examine this in our case of in our systems. Of course, this spin variance, spin texture can be studied using a perturbative approach. One can take keeping aside the spin orbit coupling part, one can consider a unperturbed Hamiltonian and put the spin orbit coupling as a perturbed component in the system. And when the electric field is present, the perturbed component can be represented through this alpha k dot sigma, where alpha forms a polynomial in terms of k, and that polynomial.
Ranjit, you have 5 to 6 minutes.
The polynomial depends on the point group symmetry of the system. Here, just a very beautiful article summarizing how the point groups makes the alpha depends on the k. So in our study, we didn't really focus on that way. We just took our effective Hamiltonian that we have developed. We further downfolded it, keeping knowing that only the top pair of valence band and the bottom pair of conduction band contribute to the spin texture. We further downfolded using a Loudon downfold. And on the bottom, the details I'm not discussing. On the bottom, I show how the spin texture becomes a function of kx, ky, kz. That is the bottom part we can immediately get from this low energy Hamiltonian. We plotted that. You see wonderful spin texture both for the conduction band spectrum and the valence band spectrum. If we take the valence band spectrum alone, we can see there are inner bands and outer bands. I demonstrated inner and outer bands. The color represents the sigma G expectation. The arrows represents the sigma X and sigma Y expectation. I apply the pressure because the pressure introduces the normal to insulating phase transition. As you can see that as we reach to a topological insulating phase transition, there are vortices that forms in the space. And furthermore, not only you see the Raspa type or Dressel's house type, you have see the plethora of spin textures which are probably not yet explored in the spin texture physics. Little more into the discussion that we know that this organic molecule sitting at the center can orient in any direction, that in principle alter the electric field in many directions. As you can alter the electric field in many directions, you can see the spiral or the breakdown spin texture or the large number of the persistent spin texture, varieties of it which can be discussed. Bringing the topological aspect and talking about bringing the topological aspects when we apply the pressure. The topological aspects brings create the band inversion where the valence band, top of the valence band enters the conduction band and bottom of the conduction band enters the valence band. That leads to creation of the vortices, which will have amazing consequence on the spin orbit transport of the system. So here is the, so now with done with halide perovskites, we can have a brief discussion on the oxide perovskites. I will only take the example of iridates. I'll talk briefly. And so here the iridate as a 5D system, here the strong correlation effect and the spin orbit effect are comparable. That gives rise to large number of states. If you look at the SR-IRO3 as a single perovskites, right? Now we are well aware of the fact that the T2G spectrums give rise to a J effective as 3/2 manifold and J effective as half manifold. J effective of half manifold creates a Dirac semi-metallic phase. There is a lot more into it. We built a multi-band tight binding model. And we saw that one of the things we noticed that contrary to the earlier assumption that only T2G can describe the band structure pretty well. Actually, in principle, both T2G and EG should be included to get a perfect band structure that matches with our density functional or electron calculation, because the oxygen plays an intermediary role which cannot be ignored, and that interacts both with the EG states and T2G states in this distorted system. And also, if you bring the correlation to picture, you can see that by playing with U and lambda, you can create metal and insulating states, different kind of magnetic configurations. The net phase diagram that we obtained in this case put into distortion and not distortion into account. We saw that in distortion, you can create a Dirac semi-metallic phase, you can create a canted antiferromagnetic state. However, in case of undistorted, all are collinear and the Dirac semi-metallic phase vanishes. I won't go into the detail of it. So then we ask the question that, you know, nowadays the people, when they study the transport, they create films, whether by reducing the dimensionality, can you create can you maintain or preserve the phase diagram that we saw in the bulk? Now, there are many ways to, there are many terminations and many ways to look at the films. One of them, the various terminations, iridium oxide, IRO to IRO2 termination, SRO termination, and one asymmetric termination. I'll just talk about the IRO to IRO2 result. If you take the IRO to IRO2 termination, Now the IRO to IRO termination can create a big space in your spin orbit coupling, and you the space spanned by the repulsion and the spin orbit coupling, and you can have a large space where the Dirac state can be reached. Not only a single Dirac state can be achieved, formed, we see a multiple number of Dirac states which are rotationally invariant in this formation. And this multiple number of Dirac states will keep increasing as you increase the layers of the films. Of course, beyond a certain limit, they will merge and form a single Dirac state. So here I conclude my discussion on the topological aspects of perovskites. I elaborated a lot on halides and gives a glimpse of the iridate oxides. If you ask me to summarize, I think I'll give a one-line summary saying that we provided a broad picture of the band topology and possible tailoring of them for halide perovskites and low spin D5 oxide perovskites. So if you ask me to put the outlook, I'll probably say that the formation of a Dirac circle, hybrid spin texture, and multiple Dirac states are very intriguing, unique, and their application perspectives in the spin area of spintronics, topotronics, orbitronics should be explored. With that, I must thank you for your attention. Here just a bit of advertisement. So we in Iit Madras have formed a perspective center, that is Center for Atomistic Modeling and Materials Design, which looks into several aspects of atomistic modeling and materials properties. Thank you very much.
Yeah, thank you, Ranjit, for the very interesting talk. And now the session is open for quick questions.
Can I ask a question?
Sure.
Mr. Nanda, it's a nice talk. Thank you. Can you hear me?
Yeah.
So in your one of the last slides, I see a lot of Dirac cones piled up, in the energy range. So I mean, all of them are actually broken inversion symmetry, right? So here, if you add more and more layers, you are not maintaining any inversion symmetry in this case.
Yeah, but these are behaving like individual independent surface states, like 2D Dirac states.
Okay.
Right?
So these are 2D Dirac states. Okay.
Yeah. They are invariant. I mean, we have a preliminary analysis of symmetry, but at least we played around the distortion and events that these are really invariant.
Okay, and all of them are maintaining the inversion symmetry in the same way, like all left.
Yeah. See, if you move from the IRO to IRO2 termination to SRO or asymmetric termination, these states do not appear. So if you want to tailor multiple Dirac states, you indeed have to maintain the symmetric terminations, that IRO to IRO2.
Okay, thanks.
So Ranjit, then I have a question.
What is the thickness of the slab that you have used for your calculation?
Oh, I see. Okay.
What?
Can you repeat the question, please?
What is the thickness of the slab that you have used for your calculation?
For which one?
This SRIRO3?
It's an ultra thin films actually. So we have taken only 3 layers, as you can see that IRO to IRO2 is a 3-layer slab. SRO is I mean 3-layer in the sense that 3 units. I mean you have 1, 2, 3 IRO2 and obviously 2 SRO. So there are total 5 layers.
I see. So because in your band structure, I don't see any bulk bands or something, because all of them look like forming the Dirac states.
Repeat?
I mean, in your band structure, all the bands looks like forming Dirac states.
So, I mean, not all, I mean, some of them are different. So this is due to the fact that each IRO2 layer, and there are in each IRO2 also, there are inequivalent iridium and oxygen complexes. Each of them now have independent bands, right? So that lead to the formation of this multiple Dirac states.
I see.
The band downfolding indeed helps.
Okay.
Yeah, so I have one last question for you. So,
Mm.
Ranjit, I think when you were talking about the alpha phase or beta phase, so in the initially, so there actually I can see that you really have a band inversion in your band. You start from a normal insulator, you close the gap and then go to a topological insulator. So with
That-
pressure, sorry?
This is the one, are you talking?
Yeah, the initial ones. Yeah, the free theories actually. Yeah, alpha, beta. Yeah.
Yeah.
Here, if I understand correctly, right? This
Yeah,
guy.
yeah. So this S and P band inversion that is
Yeah,
responsible.
right. So I mean, with pressure, do they still remain Z2 insulator?
Yeah. So, but you have to apply a substantial pressure. The question is that can you experimentally achieve that pressure? You see that I have written. I mean, you can apply around 6 to 7 gigapascal in case of CSS and CL3. I actually studied a good number of elements, all the halides, bromides, iodide, and chlorides. All of them behave similarly, but depends on the lattice parameter, the gap. Either the band gap is large or small. If it's a narrow band gap, achieving the G2 insulator with little bit of pressure, less pressure is possible. In case of CSS and CL3, you see that a pressure of 8 gigapascal can introduce a G2 insulator.
Okay. And the second question is when you go to the correlated case, for example, and if I understand correctly, they are actually from you get the Dirac surface states. So yeah,
In the correlated phase. Yeah.
correlated phases. Yeah. So
yeah, whether these are iridate family, right?
Yeah, in the iridates. So there also you are having really a band inversion like the non-interacting case.
No. It's not a bulk. It's not a topological insulator. It's just a Dirac.
I see. It's just a Dirac symmetry.
It has nothing. So this physics has nothing to do with the band insulator, right?
No, because
topological insulator.
Right. So I got confused because I thought about that. You are going towards the topological what, or is it?
No. So the halides are plausible topological insulators. On the other hand, the iridate, I mean, people have studied several other aspects on iridate.
Yeah, these are well metal also.
Yeah. So basically, we say that a couple of messages in this work. So those who are studying the model Hamiltonian way, no, you simply cannot describe the physics using the T2G manifold. The EG manifold is pretty much crucial to achieve those semi-metallic state because the interaction is iridium, oxygen, iridium, right? So, and since it's a distorted system, right, T2G and EG are not pretty much well defined, and the oxygen P states interact equally both with the T2G and EG. So, effective when you develop an effective Hamiltonian, there you include that indirect interaction into account. Hence, you have to take both T2G and EG manifold. Therefore, a 5-band model is pretty much necessary to that. And yeah, but also the other point is that which not in the context of topology, we could develop a full-fledged diagram in the space spanned by the correlation and spin-orbit coupling. And we found that many other other member of this family, basically the low spin D5 oxides, their ground state can be mapped on top of it. And the details are discussed in the paper. You can see the calcium iridate, ruthenate, lanthanum ruthenate, strontium rhodate. All are, or even barium iridate, which is undistorted, it's perfectly cubic. They are so ground state can be mapped in this phase diagram. So this phase diagram kind of tells the real story of iridate family or the low spin D5 family.
Yeah, right. Okay, thank you. Yes, if there is no any more question, then let's thanks Professor Nanda once again for the nice talk.
Yeah,
and
thank
also
you very much.
And Ranjit, one last question. I mean, do you agree if the organizers upload your talk in their website?
Yeah, they can. I have no problem.
Okay. So let me thank both the speakers, Professor Deshmukh and Professor Nanda, for the very interesting talks. And let me hand over to the organizers.
Thanks for sharing this session. So, and also both the speakers, thanks a lot for the nice talks in the morning. So now let's take a small break for 15 minutes for tea or coffee. Then let's meet again. Let's reconvene again. Okay, 15 minutes. Yeah, maybe 11:30 or 11:30. I think it's 10 minutes break. Let's meet again at 11:30. So maybe Nanda, if you're free, can I ask you a question? Okay, okay.
Hello. Hello. Oh, they have all left.
I can hear you, sir.
Can I check my slides once, please?
Sure.
Yeah. So please let me know if you can see. I am sharing my screen. Okay.
It's visible.
It's visible, and let me make it screen.
Okay.
It's working, right?
Yes, perfect.
All right. Thank you so much.
Hello.
Yes.
Yeah, this is Kansana. Can I also check it? Maybe can I share and check?
You can. You can share your slide.
Is it visible?
Yes.
The full screen mode?
I make it full screen?
Yeah, I have made it.
Yes, it has come.
1 minute. Yeah, is it moving?
Yes, yes.
Okay, thank you. So, yeah, I will stop sharing and then share again.
Okay.
Thank you.
Hi Kanchana, how are you?
Fine. Yeah. How are you, Professor Tanusri? So I will send the link and other things as and when we have the link ready. Okay.
Sure, no problem. How are you? Everything is fine?
Yeah. Going on. Only thing is like too much of administrative things now that I don't have time at all.
Yeah.
But you must be much more.
Dean.
Yeah, you are much more busy, I guess.
Yeah, being in administration, it takes quite
Actually, I told I don't want, but then somehow it has been like there was no time to even decline. That is how he posed it to me.
No, someone has to do.
Someone has to do, that is true, but I was telling like my daughter now is in 12th actually.
Oh, I see.
So it's in the, what is the heights of tension now that I have to manage everything. That's really very difficult.
I hope Vaiti is fine.
Vaiti is fine, like what to say, he is only taking major load now. Because he is in the hostel, so he only will go in between, go and check and come and all those things every day. Food and all those things. I mean, it is so, when she was so small, like just born in Max Planck, now she is in 12th class.
Right, I remember that. And now in class 12.
Time is running like very fast now. So I thought,
I do hope we can meet sometime physically.
Yeah, now I think, I mean, we would have loved to have you, physically here for this meeting, but somehow because of these things, we couldn't do it. Maybe sometime, when you are free. It's long since everyone traveled also, no?
Yeah. That's correct.
So how is Professor Indra doing?
Yeah, he's fine. He's fine. Yes.
Yeah, that's it. So, I mean, nobody is traveling. At least now, I think it is. I don't think that this is going to end ever. So we need to learn to live with Corona, I guess.
Yeah. That's true.
And this goes. The next wave is ready to come, I guess. So
yeah, exactly.
I mean, we all had one episode. So I think we now know it basically. All of us got affected at one time, so very difficult it was in between. Like
that's right. Indra got affected.
I see.
And in the third wave, and I was in isolation for 7 days.
I see. Okay.
Also because since he was infected.
Primary contacts. Yeah. That is true. But in my case, I somehow caught it from workplace or something, and then everyone, including kids and my mother-in-law, also had a wave of it. So
that's really bad.
We were really scared because she is 70 plus, no? So maybe comorbidities also, like she has this lung functionalities and all are reducing. So we were really worried. So somehow got out of it.
Right.
Very difficult times only. So that is the.
Yeah, I do hope that we can meet. We will be able to meet sometime.
Sure. We'll await it.
Okay.
Bye.
Okay. Welcome back to after the break. So now I would like to request Professor Antiferro to change the session.
Yeah. Can you hear me? Hello?
You can hear.
Yeah. So good morning, everyone. Welcome to the second session of today's second session. So there are 3 talks. First talk will be given by Professor V. Kanchana from Iit Hyderabad, and she will be talking about prediction of topological features in strongly correlated systems. So yeah, you can start your talk.
Yeah. So thank you very much, Professor Atin Pal. I will share my PPT now.
One small request, Professor Kanchana, that we are recording the videos. So I hope you are not, you are not uncomfortable with that.
Yeah, no problem.
We can record and we can upload that later.
Yes.
So I'll alert you after 20 minutes, before 5 minutes of your talk.
Yeah. No problem.
Okay, thanks.
Is my screen visible?
Yeah. Maybe you can do full screen.
Yeah, full screen. Yeah. Okay. So
thanks.
Thank you very much. Good morning to everyone. And at the outset, I would like to thank the organizers for giving me an opportunity to present my results here. Just a minute. So I would be talking about topological features in strongly correlated electron systems. So a brief introduction would be like what the quantum materials are, how do we discuss topology in condensed matter physics and classification of topological materials, and would proceed with my results and discussions. So as we all know, the materials with the properties that cannot be explained within the semi-classical limit fall into the regime of quantum materials. So materials with strongly correlated electrons and magnetic ordering, topological insulators, all will be governed by the quantum behavior, and they are falling into the quantum materials. And we know that we can classify the materials based on the band gap as metals, semiconductors, and insulators, but that is not sufficient now. And we look for a new class of materials that can make better computing. And there comes the Nobel Prize for this topological materials, which opens up new avenue and new materials, which can be used as a replacement of silicon in the semiconductor industry with the topological insulator, which can have the advantage of dissipation, less transmission of current. So this is a breakthrough, and it has opened up research in various dimensions. And the topology in geometry, if you look at, see, the sphere and the coffee mug are topologically distinct, whereas the coffee mug and the torus are topologically equivalent. So topology is concerned with the properties of the space that are preserved under continuous deformations like stretching, bending, twisting, but not tearing or gluing. So the integral of the Berry curvature over the whole surface is quantized, and that is termed as the topological invariant. Similarly, in condensed matter physics, it is nothing but the integral of the Berry curvature over the entire Brillouin zone, which is quantized, and that is called as the Chern number, which we look for. And in certain systems, where we look for the time reversal symmetry and the inversion symmetry to be preserved together with the spin orbit coupling, we look for the Z2 invariant for the two-dimensional system, where the delta I represents the parity of the eigenvalues at the trim points, and mu represents the Z2 topological invariant. The same thing for a three-dimensional system can be categorized by 4 invariants such as nu naught, nu 1, nu 2, and nu 3, designated as shown here. So now the classification can be this way, where the topological materials can be classified into topological insulators and topological semi-metals, where the topological insulators are that are ones which are insulating at the bulk and conducting at the surface. Whereas the topological semi-metals are the quantum materials with nodal points or nodal lines close to the Fermi level. Further classification of the topological materials could be, semi-metals could be the Dirac semi-metal, the Weil semi-metals, and the nodal line semi-metals, where in Dirac semi-metals, we look for 4-fold degenerate crossing points. In Weil semi-metal, we look for 2-fold degenerate points. And the nodal line semi-metals, where we look for 2 or 4-fold degenerate one-dimensional line. So some famous examples where we could see this Dirac semi-metal will be Na3Bi and CD3, where we could, where this results because of the 2 doubly degenerate bands crossing near the Fermi level at discrete points in the K-space, which is known as the Dirac point, where both time reversal symmetry and the inversion symmetries are preserved. And when either of this is broken, we land up with the Weil semi-metals. And some system host extended band crossings along special lines called as the nodal line, which can be a Weil nodal line or the Dirac nodal line. And now the flow of my focus would be on talking both about the topology and the strongly correlated system, which falls under the quantum materials. I would take an example from a d electron system and also an f electron system, and would like to present my results on that. So I start with this layered perovskite-like material, where my focus is mainly on this. First, I would like to focus on cesium MnF4. So what is known experimentally is that the neutron diffraction studies reveal that cesium MnF4 has planar magnetization and a magnetic moment of 4.04 μb. And the experimental Curie temperature is around 19 Kelvin, and it is reported to be a ferromagnetic insulator, which is quite rare. And high pressure studies reveal the magnetic phase transition from a ferromagnetic to antiferromagnetic state. And of course, there is a presence of Mn3 plus Yan-Teller ion here. In addition, the optical absorption spectroscopy studies reveals a high spin to low spin transition at around 37.5 GPa. So now this is published in JPCM. And the crystal structure details, as I told, is in tetragonal symmetry and octahedral surrounding around the manganese atoms, and experimentally reported to be ferromagnetic. So we proceeded with our ground state studies within the density functional theory, and GG exchange correlation was used to study the ground state, and strong correlation effects in this system is treated by the Hubbard U. And we have varied the U to fix up the ground state. And when we look at the mechanism which drives ferromagnetism in this system, before that we could see that this is governed by the good enough Kanemaru rules, where the ground state is driven by the super exchange phenomena between the manganese via the fluorine ions. The sign and the magnitude of the super exchange interaction between the cations depends on mainly the cation, anion, cation bond angle, the oxidation state of the magnetic cation, that is the number of d electrons present in the system, and also the symmetry of the crystal field. So we know that as per Goodenough-Kanamori rules, the interaction between the half-filled cation orbitals leads to antiferromagnetic coupling, whereas the interaction of one half-filled and empty orbital could lead to ferromagnetic coupling, which is regarded as the kinetic exchange. So we proceeded further and we vary U, and we could see that the total magnetic moment remains to be a constant and is found to be an integer value around 4 μb. So looking at the orbitals, we could see the possible super exchange pathway for the ferromagnetic ground state here, as shown between the interaction between the half-filled and the empty orbital, which is shown here. Now we turn towards the band structure. We could see that the ground state ferromagnetic insulating state is observed at a particular Hubbard U value. The semiconducting is one channel and insulating in the other channel. So integer magnetic moment of 4 μb is observed. And when we look at the orbital resolved band structure, we could see that the valence band is mainly dominated by manganese D x square minus y square and the fluorine px py orbitals, whereas the conduction band is the d z square and the fluorine pz states. So if you look at this 2.5 electron, so we started varying the correlation effects, and so we see that at 2.5 electron volt, what we observe is that the bands come closer, and in one channel we could observe a semi-metallic nature, whereas the other channel does not respond to any of these correlation effects. So we just see that there is a half semi-metallic nature observed in spin-up direction, with two bands crossing the Fermi level in spin-up channel with corresponding Fermi surfaces reflecting the hole and the electron surfaces. So the integer moment is still retained here at this Hubbard U value. And now we give a overall picture of what happens across. Like when we vary the U from 3.5 to 3 to 2.5, we could see that we are going from an insulating state to a half semi-metallic state. And at this state, we could see that the band inversion at the crossing points and a band flipping both together happening at this particular crossing points. So the manganese D x square minus square, or these are the predominant states in the valence band, and manganese D z square and pz are the ones which are predominantly dominating in the conduction band. And we observe the band inversion at the band touching points and band flipping at these two crossing points. So what else we observe is like, so when we move across, we see that there is a Mexican hat-like dispersion leading to the two nodal rings around this kz is equal to 0 plane and kz equal to 0.5 plane, which is shown here across this crossing point. So we observe the Mexican hat-like dispersion at both this gamma x m gamma plane and zr a z plane. So now we want to move further with the Vanir orbitals, and then we see the surface properties. So the presence of circular nodal rings around gamma in kz is equal to 0 plane and kz is equal to 0.5 plane is highlighted here. So we see two nodal rings which are shown schematically also in the Brillouin zone. The surface band structure highlighting the nodal lines can be seen here, which are highlighted here. And isoenergy surface also shows two nodal rings. So the non-zero Berry phase for K space enclosing these nodal lines might further validate the trivial or the non-trivial nature of the bands present here. And we also proceeded further to see if what are the other interesting features present in the system. So orbital ordering is yet another one in the magnetic systems with the Young-Taylor ion present in the system. So the orbital ordering is defined to be the spatial arrangement of different orbitals in a similar manner to that of ordered arrangement of magnetic spins in the magnetic materials. So several compounds, I mean, like could have this sort of behavior present, and KSUF3 serves as one of the example. So we proceeded further to see if such sort of ordering could be present in our system. And we could see that the charge densities highlight the dx square minus y square like orbitals with a ferro orbital ordering present in the system. So it is ferromagnetic as well as the ordering is also ferro orbital ordering, which is present. And this is the in-plane view and the out-of-plane view, which elucidates that. And we still wanted to stimulate further the ferro to antiferro transition, which is reported experimentally. So we could see that at 2.4 GPa, there is a magnetic phase transition happening from ferromagnetic to antiferromagnetic ordering. But it remains to be insulating in both the spin channels with a band gap of around 2 electron volts. And the moment is still retained here. And the manganese D and the fluorine P are the ones which are contributing in a larger amount to this band structure. Now, we want to see like what drives the transition from a ferromagnetic to antiferromagnetic state. There is a decrease in the volume and variation in the bond lengths and distance between the adjacent layers. So this leads to the possible super exchange pathway for the antiferromagnetic ground state, and which is in well accordance with the good enough Kanimari rules, where there is an interaction between the half-filled orbitals, and that drives the antiferromagnetic transition in this system. And we could see that this electronic structure, I mean, this is what is the highlight which we found here, that the topological properties are robust to spin orbit coupling, and this remains a ferromagnetic topological nodal ring half semi-metal. So we also wanted to study further what happens in potassium and the rubidium cases. So we just proceeded further. So KMNF4 is reported to be a two-dimensional non-collinear antiferromagnetic system, whereas rubidium is reported to be a collinear antiferromagnetic system. Both preserve the monoclinic symmetry, and the Néel temperatures are way lower, like around 4 and 2 Kelvin, which is reported with the presence of the Ion-Taylor ion in the system. So we started simulating, and the interesting point is like we have two non-equivalent manganese atoms present, and the equatorial and the axial bond lengths are all different in this particular cases, which was made note and which has a greater role to play because of the monoclinic symmetry present in the system. So now in addition, we also simulated different configurations. So we have A-type, G-type, C-type, and the ferromagnetic configuration studied set up for the system together with the Hubbard U. And we tried to explore the J1 and the J2 intraplanar and interplanar nearest neighbor exchange coupling constants and fit it into the underlying spin Hamiltonian model to extract the Curie temperatures using the mean field approximation. So the exchange interactions are computed by mapping the DFT total energies of each of the spin configurations, where J1 and J2s are assigned as shown here. The corresponding energies with the underlying spin Hamiltonian are given here. So now we plug this J1 and J2 into the mean field approximation, which gives us the critical temperature bit overestimated around 66 Kelvin and 56. So we find here that in KMNF4, A-type antiferromagnetic order is being favored, whereas in rubidium we could see the ferromagnetic ordering. Though the energy difference between the ferromagnetic and is very small, of several milli-electron volts, but still this is the most stable state which we could observe. But in both the compounds, the J1 is going to be higher rather than J2. So the intraplanar coupling between the manganese ions being the strongest when compared to the negligible interplanar coupling intuitively suggests the possibility for a 2D magnetism in these layered magnetic materials. So this is the highlight, like the 2D magnetism can be very well seen from this coupling constants which we have computed. So next we proceed together with the band structures. So we have plotted the band structure. We could see that in the antiferromagnetic ground state, it is semiconductor in both the spin channel with a gap of around 1.6 electron volt, and manganese dx square minus y square orbitals contribute predominantly in the valence band, and z square orbital is contributing in the conduction band. And what else is interesting is there is a flat band along this B gamma path which leads to the Van Hoff singularity in the density of states. And in addition, we could see there is a band merging at the Brillouin zone edge ZD at approximately around 0.4 electron volt below the Fermi level. So there is a nodal line like dispersion which is seen here, which needs to be validated. So we proceeded further to see that what is happening in the other path. Like, so we divide the path between gamma to B and try to see whether we could see the similar band crossings, because we could see that at gamma Z and DB, whereas what is happening between gamma B is the major important thing. So we just tried to do this and we could see the continuous crossings. So the same thing has been done in the other direction, and we see that along the ky equal to 0 plane and kx is equal to 0 plane, both we could see the nodal line like dispersion being present here. And next thing is like the inclusion of the spin orbit coupling. So we find that the nodal line is robust to the spin orbit coupling effects, and we do retain that with the inclusion of spin orbit coupling, and we can say that the nodal line like dispersion along the ZD is present. Now, the similar scenario is present in rubidium also. So in the ferromagnetic ground state, we try to simulate the band structures, and the gap here is found to be around 1.8 electron volt, and the similar orbitals contribute to the density of state as a major contribution. And the same flat bands and the nodal line like dispersion is present in rubidium also, so which is also robust to the spin orbit coupling. So now coming to the orbital ordering, we could see that visualization of the charge density highlights the dx square minus y square like orbitals with the C-type orbital ordering here. In both the compounds, we could see that an antiferro orbital ordering within the AB plane and the ferro orbital ordering out of plane is seen here, which predominantly favors the C-type orbital order present in this system. So this is the highlights coming out from this. Like we need the latest magnetic studies to resolve the controversies present between the rubidium and the potassium. Though belonging to the same symmetry, we don't find the same ground state. So we need to look for the latest neutron studies, and the orbital ordering which comes out has been reported in these compounds together with the 2D magnetism which can come out of this. Next, I would proceed ahead with the F electron system. So we want to discuss ytterbium, cadmium, tin. So the evidence for the large magnetoresistance and mass enhancement present in the system. So in general, topological, when we take topological semimetals, they are well known for the extremely large non-saturated magnetoresistance, chiral anomaly, and the anomalous Hall effect. Similarly, when we move ahead with a strongly correlated system, one will look for valence fluctuation, Kondo effect, and heavy fermion behavior. So now here it is a combination of both, and we would like to see the effects present in this ytterbium, cadmium, tin. So experimentally, the electron correlation effects were verified by two measurements, the magnetic susceptibility and the specific heat. And here, interestingly, the effective magnetic moment estimated from the Curie constant is around 2.61 μb, which is in between the values for ytterbium 2+ and ytterbium 3+, which typically shows the nature of intermediate balance present in the system. So further evidence is also drawn from the specific heat values, which again supports this fact. And also a large non-saturating magnetic resistance is also, MR is observed at 4 Kelvin in magnetotransport analysis. So the possible origin could be the electron hole compensation effect, which is seen here, which is also observed in our studies through the semimetallic nature present in the system. So we started simulating this thing with the hexagonal symmetry with the space group 189. And the major symmetries include the 3-fold rotation axis and the horizontal mirror plane, which is similar to calcium, cadmium, germanium. And when we look at the band structure, as we had the intermediate balance, so we could not simulate the intermediate balance, but we did our calculations for ytterbium 2+ and ytterbium 3+ to fix up the ground state. So the self-consistency LSDA calculations as a function of volume were performed to find the ground state after realization of the two relevant configurations, namely the 2+ and the 3+. And we see that ytterbium 2+ is found to be energetically more favorable. And the spin decomposed density of states also illustrate the semimetallic character in ytterbium 2+ state, which again is in favor with the experimental finding of the charge compensation. And when we look at the band structure, we could see the bulk band structure with and without SOC for the ytterbium ground state. So valence and the conduction bands meet at, like around the 0.03 electron volt in the gamma M direction and at 0.01 in gamma K direction. So the band inversion across the crossing points between the cadmium S and the tin P states suggests like the nodal line present around the gamma point. So now when we look at the surface states, the surface band structure highlighting the nodal line with the presence of drumhead surface state emanating from the nodal line can be seen here along with the hexagonal nodal ring. So because of this band dispersion and the inversion, we proceeded ahead and we could see this. And so these are the predictions which come out of this. So there's a prediction of energy ground state, which is ytterbium 2+, which is in favor of the experimental findings. And we also predict a possible nodal lines semi-metallic state in ytterbium, cadmium, tin. Now we proceed further with the europium gold arsenide, which is again in a hexagonal structure and the space group of 194.
Professor Kanchana, you have 5 more minutes.
Yeah. So we see the A-type antiferromagnetic system, and this is non-symmorphic again. So we have done in conjunction with the experimental studies, which is going in line with our experimental findings. So we could see that there again, there is a band crossing and the Dirac-like linearized point can be found at the gamma point, at A point. And this further was confirmed through the surface states, and we could see a drumhead surface state, and which is verifying the findings. And we also have done gone beyond, and we could see that topology and spin together can lead to topological spintronics, which can be seen as anomalous Hall effect, manifesting in anomalous Hall effect and the Nernst effect. As we all know, the interplay of magnetism and topology opens up the possibility for the linear response effects, such as the Hall effect, anomalous Hall effect, and the Nernst effect. So this can be found in solids with broken time reversal symmetry, typically in ferromagnetic phase, as a consequence of spin-orbit coupling. So what is special here is that in ferromagnetic materials, Hall resistivity includes an additional contribution known as the anomalous Hall effect, which depends on the magnetization of the material and is much larger than the ordinary Hall resistivity. And this mainly, there can be an intrinsic and an extrinsic contribution to this, but we focus more on the intrinsic effect, which can be seen from the Berry curvature. So it is a geometrical property, which we have already explained, which encodes how the eigenstates evolve as a local function of parameters. So now also we studied the Nernst effect, which is nothing but, which can be seen as a thermoelectric counterpart of the anomalous Hall effect. So now when we move ahead, so we can just have it in a nutshell like this. Like, there is a symmetry breaking depending upon the direction of magnetization leads to wild point, and this can be inducing a large Berry curvature in the vicinity of Fermi energy, and that can lead us to the calculation of the AHC and ANC. And this has several applications. And now when we look at our case, we have done the same thing, calculation of the anomalous Hall and the Nernst conductivities in a Heusler compound. So we simulated the system, and we could see the band structures, and which leads to the half metallic nature with the two bands crossing the Fermi level. And we proceeded together, to include the spin-orbit coupling effect, and we could see the band crossing points lifts up degeneracy with spin-orbit inclusion, which hints for the analysis of the topological nature. So we also studied the exchange interactions and the Curie temperature using the Heisenberg's model and fitted it, and we could see that the nearest neighbor interactions of the dominating contribution could be mainly from cobalt 1, cobalt 2, and the next one would be the cobalt 1. And so there is a very, the fluctuating oscillatory behavior could be found, which really indicates the RKKY type of interaction present in the system. And our estimated Curie temperature is around 351. For the experimental 351 value, we could see 548, which is a bit overestimated, and that generally happens in the main field approximation. And in addition, we do find a discrepancy between the experimental value and our computed thing, which is a half metallic system, and we find a 2 μb magnetic moment, which could be mainly due to the disorder present in the system. And we have simulated 2 types of disorder, which is the B2 type and D03 type. And the B2 type disorder is the one which is leading to the discrepancy. And we could see that the B2 type disorder present in the system may be the reason for the variation present between the experimental and the theoretical computed values. And we also proceeded with the Berry curvature alongside those. The peaks and the valleys indicates the anomalous Hall conductivity present here, and we have tried to plot the anomalous Hall conductivity and the Nernst effect also, and this can be seen from the plots here. And the large Berry curvature gets induced because of the spin-orbit coupling effect, and the non-vanishing valleys and peaks with the inclusion of spin-orbit coupling leads to these effects. Consequently, with the manipulation of the symmetries in the band structure, one can try to tune this thing, and the Berry curvature and the intrinsic AHC and ANE can be restrained, which is independent of the finite value of magnetization. Though we have the values bit away, we can always try to tune this. And our values for this compound is shown here, which is in accordance with the values present in any other Heusler alloys. And in addition, we also tried to proceed ahead with the pressure effects, and we studied the mechanical and the dynamical stability of these systems under pressure, and which is given here. We could see the positive modes at 5, 10, and 15 GPa as well as at ambient. And we were curious to know what is happening with the electronic structure as well. So when we apply pressure, we could see that there is a half metal to metal transition happening under pressure, which is evidence to the Fermi surface topology here. We could see that there is a change from the half metallic system to a metallic system here. And the variation of magnetic moments, etc., are given here, though there is a drop. And so the magnetic moment changes from the integer value to value of 1.98 μb as the pressure increases. So the variation of ANC and AHC for different pressures as a function of energy is given here. And what we observe is like a maximum for different pressures, the energy range of 300 milli electron volt is what reported here. So the maximum value decreases. The AHC increases from 0 to 15 GPa, whereas the ANC value, we could see that it systematically decreases from 0 to 15 GPa. And the Curie temperature is also computed. We could see that the variation of Curie temperature increases up to 10 GPa systematically, and then there is a decrease. So we can say that under pressure, it is not suitable for spintronic application as it loses its half metallicity, whereas AHC, ANC, there is no big change and it can be retained in that range. So the highlights is like it's found to be half metallic and ferromagnetic in nature via the Heisenberg exchange interaction, and the non-vanishing peaks and valleys of the Berry curvature together with the spin-orbit coupling results in the intrinsic contribution to the AHC and the ANC. Under pressure, the maximum values are almost retained and there is no big change is what we could say from 0 to 15 GPa. And with this, I would like to acknowledge my graduate students who contributed to this work, and also the experimental collaborators, Professor Zakir and Dr. Manivan from DMRL. And I would also like to thank IIT Hyderabad for the computational facilities, and also the funding agencies for the grants, and the CDAC for the computational facilities. And this is my group, and thank you for your attention.
Okay, thank you, Professor Kanchana, for a very nice talk. So now the room is open. First, from the online participant, anybody has any question? Or from the offline?
So I have one question.
Yeah.
In last few slides, you have compared 3 compounds where you got the nodal line. So can you please say that which symmetry is giving you this kind of nodal line, and what is the and how do I break that kind of symmetry? Then how do you say that this is non-topological? I mean the topological.
Which compound are you talking about?
The first slide you compare 3 compounds. So where you are getting the nodal ring?
You are talking about first compound or what?
I think.
Can you tell me the slide number otherwise?
The slide number. So in where you are getting the nodal line, I mean not hexagonal, the first one. So,
yeah, this one?
Yes, yes. So here you are getting nodal line, and then which symmetry is giving you this nodal line?
I mean, I could just see that, I mean, the symmetry, I mean, it is robust to spin-orbit coupling, and I mean, from the band dispersion path, I can see that there is a continuous, the dispersion which is happening around gamma to B. That is what is giving the nodal line here.
Okay, the spin-orbit coupling is breaking the nodal line?
No, it is robust to spin-orbit coupling. That's what, even with spin-orbit coupling, we can see the nodal line here.
So, is there any kind of process that you can break which is giving you this nodal line? So,
we haven't tried. Maybe we have to apply the external stimuli, maybe the strain or something which can try to break the symmetry, which is preserving this nodal line. So maybe I have to explore that, which we have not done so far.
Okay. This nodal line is topological or non-topological? Then how can you define? I mean, is there any Berry curvature corresponding to that line?
No, we can do that by analyzing the band. I mean, the inversion and the band inversion happening at that point will definitely tell that it is topological. I mean, band mixing and band inversion happens at some point. Then we can always tell that it is going to be topological. But all what we observe here at the moment is it is still in progress. So we could see that there is a nodal line present here.
And
maybe we can discuss later or something, because we are so there is a question by Gaurav. Gaurav, please unmute and ask.
Yes, hello.
Yeah.
Yes, ma'am. So my question is, ma'am, which software you have used to compute the anomalous nudge conductivity?
We have used the ground state. Another thing is through VASP, and then we have gone for Vanir tools. Using the Vanir tools, we could try to compute that.
Anomalous nudge effect as well, ma'am.
Yes.
Okay.
Okay. So the next question is by Professor Shahadash Gupta. Yeah.
Kanchana,
yes.
I have a question concerning your first set of compound, where you have the difference between the rubidium and the cesium.
Yeah.
So have you really, because nothing much really changes, you have the same crystal structure, you have manganese and fluorine, same, sorry, it's between potassium and rubidium. So have you really checked the covalency between potassium and fluorine vis-a-vis rubidium and fluorine? I mean,
yeah, it's a good question. Like we were also puzzled, like we thinking like why, because when the symmetry remains the same and nothing else is changing, so why it could be so. As you told, we are trying to look into that thing, and in addition also include the next nearest neighbor and try to simulate further more patterns which can try to help us give an insight into this. because we also expect the same magnetic ordering to be present here, but that is what we are trying to analyze. But as of now, we had this result, so I thought maybe we need to explore further on this.
The other related question is that these numbers, especially J2, are so tiny, it is actually at the borderline of DFT accuracy limit. So how sure of the sign of the J2 for especially for potassium compound?
Yeah, but that I have checked it. It is coming to be that low only for us because the energy difference and what we have between different concentrations.
No, that is perfectly correct. But the difference between potassium and rubidium, of course, the strength of J's can vary. But what is more different is the sign of J2.
Yeah.
So how sure you are of the sign of J2? Because it's very, very tiny number, 0.0074. So instead of minus 0.0074, it could have been plus 0.0074.
Yeah,
you cannot distinguish between the two. It's so small.
Yeah, that is correct. So maybe what I can do is like to have it as a bigger supercell and try to compute it to see whether if we land up with the same values or not. So maybe at least of the same order. So we are trying to continue that, and maybe I can give you a better answer then.
Okay, thank you. Thank you for your nice talk.
Yeah, thank you.
Okay, the quick last question by Shudipto Chatterjee.
Ma'am, I have just only small query that for a normally half metallic system, you normally see there is a negligible pressure dependence of the Curie temperature. Okay, so for your case, for the CO2 NBGA sample, I can say that there is a pressure dependence of TC. So is that because of the disorder present in the system that you were saying?
Of course, yes, because as I told, even to simulate the ambient case, we have to include a B2 type disorder, which again is 50%. So I would say that, maybe first thing is like this much pressure correlating with the experiments may not be possible. But as you correctly told, disorder is a major thing which drives this type of anomalous things present in the system.
Okay. So if there is no other question, let's thank the speaker again. For the very nice talk.
Thank you.
To the last talk of this session, and last talk will be given by Dr. Rajiv Bhattokwal from UGC DAE Consortium for Scientific Research, Indore, India, and he will be talking about protection and manipulation of topological states at the boundary of wild semimetals. Yeah, Dr. Rajiv Bhattokwal.
Yeah, thank you, Atindra, and thank you to the organizer for giving me the opportunity to share our work. Can you see my screen? Maybe?
Yeah, we can. It is visible. Just please make it full screen.
Yeah. Now is it okay?
Yeah.
Full screen.
Yeah.
Okay. And hi. So I am Rajiv. Today I am going to talk about the protection and manipulation of topological states at the boundary of wild fermions, wild semimetal. So the outline of my talk will be as follows. First, I will talk about a little bit about the topological phases of matter, and then I will explain the experimental technique that we adopt to measure the states, is basically scanning microscopy and spectroscopy. And then I will show you two contradictory behavior of the Fermi arc that coming from the wild semimetal. In one case, we probe the topological protection in inversion symmetry broken wild semimetal, and in the other case, we'll show you how these topological states are susceptible to the surface potential. And in this case, we probe this in time reversal breaking semimetal cobaltin sulfate. So to start with, the first realization of topological phase was the integer quantum Hall effect, and probably many people just touch this topic. I will not spend much time here. So basically, we take a two-dimensional electron gas and apply magnetic field, and perpendicular to it, and as a consequence, we get these Landau levels. And in the material, what happens is basically the electrons will be filled up until certain Landau levels, and will be is separated by energy gap to its conduction level, and we get electrons in a cyclotron motions. So now the interesting thing happens if we go very low temperature and high magnetic field and measure this the resistivity along x and resistivity along y. Then basically two surprising results comes. First of all, the green one is basically rho XX along longitudinal resistivity, and it shows some zero value in some interval of the magnetic field. However, and in another case, the Hall conductivity, which is basically Hall resistivity along this y direction, it takes exactly in that place of magnetic field, it shows a constant value or as a Plato kind of thing. So basically, and when if we consider the conductivity, Hall conductivity, and it turns out to be it's basically some integer times e squared by h, where E and h is a fundamental constant, electron charge and Planck constant. And in this experiment, this n has been measured very accurately, and this accuracy is the order of 10 to the minus 9. So why this is happening? So first, I like to answer this rho xs, why this resistivity goes 0. Its answer lies at the boundary. So when at the boundary, what happens? The electron cannot make this circular orbit, this circular formation orbit. Rather, it forms a skipping orbit, and you get a edge mode at the boundary. And this is the mode that gives some conductance, but it doesn't tell us why the resistivity. It can give the resistivity can go non-zero value, but go reduce or go down, but may not be. It cannot give the resistivity zero. But another interesting thing happens. So if you consider within this gap, for example, within this, if we tune the magnetic field in such a way that if the bulk is within this gap position, and if you have this edge mode, then what happens that basically if you put some impurity or some scattering center from which the resistivity or resistance comes, then basically there is no other state for electron to scatter back. So basically what it will do, it will just keep it and it keep going in forward direction. And this is the reason why the whole the separation of this scattering and hence resistivity goes down to zero. But why this number, or why in this Hall conductivity, why this number comes? So basically its answer lies in the definition of the topology of the bulk band structure of this material. And we all know at this time that this is the Chern number, and Chern number actually this can be calculated as in this equation. So this equation basically it guarantees us that if you take the wave function of the electrons in the momentum space and you just solve this integral, it gives us an integer value. And if it is a 0, then it's a trivial insulator. But if it is a non-zero, then there's a topological phase change, and it turns out to be a topological phase. We call this quantum Hall phase, and this is exactly the n, the number n. It comes here in this equation. We measure that, so that's why it is very accurate. And this was this experiment and this theory has been awarded Nobel Prize in 1985 and in 2016. But very interesting properties this electron has. Actually, they are unstoppable. No U-turn is possible and insensitive to disorder. So now I'm going to tell you another kind of topological class is basically wild semi-metal. So in order to start the wild semi-metal, I would like to tell you about the Dirac semi-metal. So we get Dirac semi-metal whenever two degenerate band in conduction band and valence band cross each other in momentum space, and these bands must be degenerate because electrons are spinful and it has a spin flavor, both kind of spin flavor. But if the crystal or the environmental situation applies some perturbation, and if this perturbation actually mixes the spin structure or the helicity of this band, then it opens up a gap and converts it as a normal insulator. But if in certain cases, if there is some symmetry, it may be crystal symmetry or other kind of symmetry, which basically doesn't mix this the spin structure of the or preserve the helicity of this band, then basically then this band crossing is get protected, and in reality we get Dirac semi-metal, for example, cadmium or silver. But another trick we can apply here. So if we apply some symmetry breaking perturbation, then what it can do, it doesn't mix the helicity, but basically it shift this, leave the degeneration and shift apart of these two degenerate bands in momentum space. And this is what exactly the symmetry breaking perturbation can do to this system. And so basically, and we get the wild semi-metal phase. So basically, wild semi-metal phase is nothing but the Dirac semi-metals, where the helical symmetry, the degenerations get lifted by induction, inversion, or time reversal symmetry. So the crossing point of these two bands are called wild nodes, and near the wild nodes, the electron has very linear dispersion in all three momentum directions. So basically, it's like a 3D Dirac cone, and is basically act as a source of sink of the other a curvature. So curvature actually comes from the curvature of the wave function in momentum space, and it's called Berry curvature. And what it happens is basically Berry flux actually emerging from one node and propagate through this curvature to the other node. So now if you consider a two-dimensional plane in this three-dimensional momentum space, and what happens is basically, and if you calculate the Chern number, exactly the Chern number what I showed you for the case of quantum Hall, and it turns out to be non-zero. And non-zero Chern number tells us to find a chiral edge mode if you produce the boundary. So now if you just slide this arbitrarily chosen 2D plane in 3D momentum space and collect one by one this edge mode, so then basically it forms a two-dimensional surface state at the surface or the boundary of the crystal, and it's a topological state, and we call Fermi arc. So basically, and this Fermi arc in one surface has an open contour, and the other contour goes to the other surface of this band. And you can think about that. This is the while phase is nothing but a quantum Hall physics, but it is a three-dimensional analog to this two-dimensional quantum Hall phase. In quantum Hall phase, we induce topology by applying magnetic field, but here strong Berry curvature, Berry flux near these while nodes actually plays the role of this magnetic field and turns this material to a topological semiconductor. So another interesting part I will come to in later my talk. If we ask the question, how much the surface states are localized on the surface? So the localization or the penetration depth of these states actually depends upon at that particular moment how much band gap it sees in its bulk. So for example, in this position where the band gap in the bulk is higher, the penetration depth is low. As one goes towards the while nodes, then this penetration depth diverge. And basically, this gives a very interesting interplay between surface and bulk state in this material. So now let me tell you briefly about scanning channel microscopy. And in STM, basically we bring a very sharp tip to a sample surface, atomically clean surface samples, and measure the tunneling current. And we can measure the tunneling current as a function of x and y, which can give rise, basically give rise the topographic image. For example, copper 111 surface, as I'm showing you here. But under certain approximation, we can go a particular position and measure the voltage derivative of the tunneling current, which is proportional to the density of state of the sample. And for example, here I'm showing you point spectra from copper surface, and it is revealed these surface states, characteristic surface state on top of this bulk band, bulk density of states. But one more thing we can do. So what we can do, so for example, think about if we have the impurity, and that impurity could be adatom or vacuum or stacking fault or any or the state, any kind of the crystal imperfection that actually breaks the translational symmetry. So and basically that acts as a scatterer to the surface electron. So basically surface electrons scatter in presence of this impurity in such a way that the incoming wave and outgoing wave interfere each other and give rise to interference pattern. And this interference pattern comes in the density of states. And this as a name is called quasi-particle interference. And we measure density of states as a function of space and also the energy in STM. So we can measure that. And every interference pattern is associated with as a wavelength. And if we just Fourier transform, then you get information of the scattering vector in momentum space. And if we do it in different energy and project it in one particular momentum direction, then it exactly mimic the energy dispersion of these states. So for example, here I'm showing you one Nelson spectra of copper, where it is the dispersion of the copper band is probed in momentum space, or in the actually it's a scattering space. But if you go to the 2-dimension, is the same, and the technique can be implemented, and you can dig more information about electronic band structure of this material. So this is the tools, in short we call QPR measurement. So this is the tool we will be using to probe these exotic topological states. So now let's see some data. First, inversion symmetry broken wide symmetry was realized in tantalum arsenide and its material families. And unlike the example I showed where I show you only 2 while nodes, this material has 24 number of while nodes in its period. And among them, 16 are get projected on 001 surface at which we measure. And the connecting line between the while nodes are the Fermi arc. But apart from this Fermi arc, the surface also hosts the trivial band, like ellipse band, bow tie band, and some trivial bands near the Fermi arc. So it is a challenge as well as an opportunity to probe these topological bands from the sea of these trivial bands. And in order to do that, we measure in STM and we measure also the QPI. So here I'm showing a topographic image of tantalum arsenide 001 surface, where this single atom vacancy is decorated all over the surfaces. And if we go to the clean image, clean area, and do the high resolution microscopy, it shows the square lattice structure of the crystal. We go to this clean image and also do the spectroscopy, point spectroscopy DI over DV, and compare with the calculated DOS. In one time, we calculate an arsenic termination, another time is tantalum termination, but our data matches very well with this arsenic termination. So the surface we are showing is arsenic terminated surface, and these are the arsenic single atom. As I told you before, that the electron on this surface actually sees this impurity and will scatter in such a way that it will form the interference pattern, the QPI. And this QPI appears in density of states, and hence the DI over DV that we measure. And this is the elongated puddles near the impurity center. This QPI appear. And in order to understand what is the band involved in the scattering processes, we Fourier transform this and we get QPI in momentum. So this is a very enriched QPI pattern that I show here. And also, since it is a spatial resolved measurement, now you can define the Brillouin zone. So for example, this is dotted line, this is the first Brillouin zone, second Brillouin zone, and so on and so forth. The higher Brillouin zone. So now what we see is a very prominent QPI feature at Q equal to 0 as well as throughout the Brillouin zone. So in order to understand that, here I'm showing you the calculated band structure again. And what we do basically that we measure the scattering. So in theory, we took this calculated structure and we also calculate the joint density of state. That means we allow all the possible scattering that can take place from all this band. Only the restriction we put that two different spin cannot scatter themselves to their bands. For example, off spin only scatter to off spin. So this is a spin selective scattering probability. And if we calculate and consider the scattering within the ellipse band, we get these blue patches. Within the bow tie band, we get these yellow patches, and we see this blue QPI feature here, and very faint this bow tie feature that in the yellow-like band, and also the green one, which is basically bow tie to ellipse band scattering that appears in the corner. So these are all trivial band scattering. But of course, we are interested to know, is there any scattering takes place from the Fermi? So in order to do that, I zoom in and we see that there is a leaf-like pattern just appear beside this ellipse band. And when you compare with our calculation, it immediately tells that it's attributed from the scattering between this Fermi arc to its trivial tail. So at this point, we show this Fermi arc scattering and hence Fermi arc, and we establish that tantalum arsenide is a wild Fermi arc. It hosts a Fermi arc. Now I'm going to go back and what we see here in the whole Brillouin zone, we see very abnormal and very crazy QPI patterns in the sense that few of the QPI, for example, this bow tie QPI appears very faintly at the center. It replicates to the Bragg peak strongly. Similarly, the ellipse band, half of it replicates strongly, half of it very faintly. So we would like to understand why it is happening. So one reason is that since our impurity is in a single atom length scale, so one can think that the impurity potential can make this replication towards near the back. But when we go far from the impurity section, it's a clean region where there is no scatterer, we found the real space density of state actually gives this modulation. And this is the reason why we see the back peak in density of states in QPI. So basically, and we also notice the modulation of this di over dv, or this density of states in real space, and this replication in momentum space, they disperse in a very correlated manner as a function of energy. And so that must be not coming from the scatterer or the impurities, but it is a property of a wave function. So far, we have considered only the first Brillouin zone, and the density of state is considered, is defined as the wave function times its dispersion. And we know when you have a periodic crystal, we have to take the block wave functions. And block wave function contains this block coefficients, which basically replicate throughout the Brillouin zone. And this value, these coefficients are not random. and is not constant, rather it is a part of the dispersion of this electron band. So now when we plug this equation with this density of states equation, it immediately tells that if in this Bilayer zone, if there is two dominating coefficients, the block coefficients, then the QPI or this density of state can be modulated exactly by that reciprocal lattice vector that connects them. And similarly, if this band carries some interference pattern, that will also be replicated at the QPI exactly by that reciprocal vector. So now let us see. We calculate this coefficient for ellipse band, which is a trivial band, and if we found surprisingly that the center Bilayer zone has a dominating coefficient, this is subdominating, less dominating, and essentially the coefficient is nearly 0. So now, if the strong QPI scattering feature that comes at the QPI in the experiment, it only happens when it involves two bands which has a very dominating coefficients. But if you consider two subdominating coefficient scattering, then the other fainter half of the ellipse comes. And if we go along to the y-axis, where this value is negligibly small, we hardly see any replication of this ellipse band. So this trivial bands looks like it has a very complex block structure. And but what about the Fermi arc? So for the case of Fermi arc, we see is only one strong and dominating coefficient at the center, and they are isotropically distributed, and the value is very less for the other Bilayer zone, and they are isotropically distributed. And for the in the same time, at the same time, we didn't see any replication of this Fermi arc scattering near this graphene. So basically, this Fermi arc wave function has a plane wave-like wave function. As we know that plane wave can appear in vacuum, so it doesn't know about these crystal details on any disorder that's present on the surface. So in that sense, these states are very protected against the surface potential. So now I'm going to go to the second part, where we measure the wild semi-metal phase in the ferromagnetic material, and which is basically cobalt and sulfur. And in this material, the tin and sulfur in its lattice structure has a triangular lattice structure, and the cobalt is in between them, and cobalt has a very interesting Kagome lattice feature. And at below the Curie temperature, this is a ferromagnet below 175 Kelvin, and if the spin actually they interact ferromagnetically, and we are measuring at 4 Kelvin. So basically, we are deep in ferromagnetic phase. But in calculation, this material actually was predicted to be a wild semi-metal, where the 6 number of wild nodes present in the Bilayer zone, and all of them get projected on 001 surface, and this is the surface at which we are measuring. But before we start experiment, there is some indication that the material could be a ferromagnetic semi-metal from the magnetotransport experiment. For example, there was a signature of anomalous Hall effect, which basically without magnetic field you get Hall effect, and this is due to the strong Berry curvature, Berry flux that that these wild nodes host inside it. And there is a chiral anomaly, which is basically magnetic resistance, negative magnetic resistance as a function of magnetic field. This kind of these properties actually sometimes assigned to the wild fermion, but we carry on experiment to spectroscopically visualize this wild phase, and also we show this classification, new classification here. So basically, here I'm showing you. So in cobalt tin sulfur, when you clip the sample, it can all 3 terminations can be possible can be accessible with STM. And here I'm showing you only the tin surface, and this is again the real space QPI measurement. But real space QPI measurement, the oscillation was not very much understandable. But when in Fourier transform, we show you here QPI in momentum space, one in 7.5 eV, above milli-electron volt above Fermi, and one is below Fermi. So what we see a very strong geometric QPI pattern, this hexagonal pattern at the center, and that replicates near the back peak. But when we go down to energy, the size of the hexagon increases, and at a particular energy that gets connected. And this is how it styles the whole Bilayer zone in momentum space, and momentum space. And in order to understand which is the band again to involve in these processes, we compare with our calculation, which actually allow us to identify the position of the wild nodes, and also which bands are the Fermi arc. And what we see, only this triangular band at K, apart from these are the Fermi arc, and the rest are all trivial bands. And if we go from this energy to below in the energy, then basically this to get this hexagonal QPI, basically that scattering just takes place from this trivial band to this pocket, triangular pocket at K, and also the K prime. And this is how it completes this hexagon. And then if you go down to energy, then the internal trivial hexagonal band gets shrink, and also this triangular pocket gets shrink and making this scattering vector larger. So this is the reason why this QPI gets
Rajiv, you have five more minutes to finish.
Okay, sure, I will come. So basically here, when we compare this calculation, it immediately tells this to gauge this hexagonal pattern, it must involve the Fermi bands. And in this way, we show this while phase here as well. But can you tell something about the time reversal symmetry breaking in experiment? So in time reversal, what is time reversal breaking? Time reversal symmetry is basically, it tells us that if it's a preserving system, then you get, if you have a band, it must have a time reversal partner exactly at minus K. But if you look at the calculation, it already tells us that the band at K and K prime, they are not symmetric. So there must be time reversal broken in theory, but when we compare our experimental results, so what we do a line cut along K, gamma, K prime, and I'm showing you is a basically energy versus the scattering vector. And if we zoom in and just subtract this strong background, then it immediately tells us that there is actually two parallel bands with two different Q vector. Their dispersion is a function of energy. And when you compare it, actually it can only come from if this K and K prime position are different. And if it is a time reversal preserving system, then this band we should see only one band. So here we see two bands, so it establishes that the material is time reversal broken system. So now I'm going to show you the other termination. What happens in the other termination? So basically we saw, and since tin and sulfur both has a triangular lattice, it was very difficult for us to identify them. But by seeing this the hexagonal Kagome structure in one of the facet, we immediately identify this is the cobalt. But when we compare the step edge with this cobalt layer, then we see we immediately and compare with the crystal structure that immediately tells us which are sulfur and which are tin. Moreover, when you do the point spectra, it shows three different termination has three distinctly different spectroscopic signature, and however they are sharing the same bulk. So it immediately tells that the surface potential plays a crucial role in determining the band structure of the surface. And again, we perform QPI measurement in all the surfaces. We also see distinctly different the QPI feature in this in the different termination. And I'm not going to the details, but in all termination we show the Fermi scattering. But I'll show you something more interesting. Actually, depending upon the surface potential, the connectivity of this Fermi gets changed in this material. So in the first case, I show you the tin. This is a schematic diagram. And in case of the tin, the Fermi arc connects two wild nodes within the Brillouin zone. But we can consider a trivial band which can hybridize with this Fermi arc, and it can change its contour and energy and dispersion. So basically, this is exactly what happens for the case of sulfur, but we come out a very disappointing way because in the sulfur, whenever this Fermi arc coming from these wild nodes is immediately hybridized with this trivial bands, and basically it doesn't offer us to measure this connectivity. However, we can think another triangular band like this, and after hybridization, it shows something interesting. Actually, it also changes the contour and the dispersion, but it changes in such a way that the connectivity gets changed. Now the connectivity between two wild nodes by this Fermi arc is between two different Brillouin. So this is the exactly things that we see in cobalt, where we find this inter-Brillouin zone connectivity. And as I see here, these all the bands are very much susceptible to the surface potential, and there's a topological band, so it can offer to manipulate this topological phase, a topological band with choosing proper surface potential or surface impurity. So now let me reconcile these two contradictory the properties that we have found into different kind of wild same metal. In time reversal broken wild same metal for the case of cobalt in sulfur, what we see is basically is a varying dispersion, and it can connect, the connectivity of the wild nodes gets changed depending upon the surface potential or the surface termination. However, in the case of inversing symmetry broken tantalum arsenide wild same metal, we found that the Fermi arc is very much robust and they are insensitive to the surface potential. So what we think that basically this reason, actually the reason behind it is hidden in the penetration of the surface. As here we see for the case of tantalum arsenide, here the separation between the wild node is very tiny, and also this gap is very low. So basically the surface state gets penetrated much larger than this compared to this cobaltine surface. So basically the surface state which lives more in bulk, they gets very little the overlapping function to interact with the surface or its potential or surface wave function. But in the case of time reversal, this case, what we found is that the penetration only driver near the wild node, but most of the states lives on the surface and then interact strongly. And before I must acknowledge our colleague at Weizmann, sorry, my students in the Weizmann Institute with whom we work, Noam and Pranav, and I was our supervisor and we was a scientist in the lab. And the theory is done by the Binga Adi Stern, and Hugh. And also the sample was fabricated by the Claudius group at Max Planck Institute. Thank you very much for your attention.
Thank you, Rajiv, for a very nice talk. So now the room is open for question. So first from online participant, Dr. Gautam Sheet has a question. So please carry on.
Yes. Could you please show the conductance image from which the QPI pattern is generated?
Yeah.
Yeah.
You mean, okay, so it is a...
Yeah, there are many. So
yeah.
The conductance map. Yeah.
Yes. You mean for tantalum arsenide, right?
Yeah, tantalum arsenide.
This one?
No, the one that you used for QPI, the one for which you did Fourier transform and got the QPI bands.
Yeah, so this is in this slide, actually, this is for tantalum arsenide. This is the topographic image, and now this is the QPI, and now this is the QPI in Fourier space. So you mean this one, right?
Yeah, this is the QPI in the Fourier space, but please go back to the previous slide. So yeah, so if I zoom into one of these little things, so these are the defects, and you have the pattern around the defect, right?
Right.
Yeah. So, but that is then. Do you select only that part? Means how do you get the Fourier transform from this? Are there, means is this the raw image that shows the ripples? For example, I do not see those quasi-particle interference ripples. Where are they? So
yeah, so you know what? If you, it is very difficult. I mean, because there's the multi-scatterer here. Unlike the case of copper, where you see very systematic. The circular QPI. But due to this multi-scatterer and also the shape of the wave function and how they interfere. So this is the way. That's why you are not seeing very clearly. But if you go back a bit, and then you can see this this thing. And this is why you actually go to the Fourier space, which actually is show you QPI in very good manner actually,
so,
and very neat and clean image.
If I look at this picture, you have very sharp Q vectors. That means corresponding to those Q, you should have those modulation in the real space that should be visible, no?
Yeah, so basically, yeah, so if you choose here, so because you see here, you have many Q vector here, and there are many kind of oscillation involved in this process. Now, if you choose any particular this one and compare, and just go to the real space and only choose that particular wave vector, then you will get that oscillation. But actually in real space, when you measure, all the Q will come and they will interfere each other, and you will get a very complicated interference pattern. So that's why it is very difficult to treat.
Yeah, so I'm slightly surprised because I do not see any interference pattern here. It looks like it's
no, you don't see these elongated puddles here.
Something, yeah.
You
Okay,
don't see
okay.
this
So
elongated particles, for example.
Yeah, maybe I
Yeah, if you go back, or maybe the color scale was not good enough.
Okay, okay, thank you. Yeah.
Okay, so the next question is by the.
So I think a small clarification.
Yeah.
Is this the raw image, or was some processing done from the raw image?
No. This is raw image, and this is also raw image. But for this one, to make this, actually we find, so the symmetry operation has been done. So first, when you do this, the Fourier transform, raw Fourier transform, then you will identify all the scattering. First, you have to identify that, and if see all the scattering is real, then you can do the symmetry operation. So that means it has a fourfold symmetry, and then you do symmetry operation. It shows a bit more good way. But you can find in raw image all the scattering that I'm showing you here.
So some processing was done, some symmetrization was done.
Yeah, symmetrization done, provided all the Q vector that you see, they are in raw data. And this is in supplementary, you can find that raw data as well.
Oh, okay, I will see that. Okay, thank you.
Okay, so the next question is by the offline participant.
Yes, please.
Okay, I have actually I have several problems.
Okay.
Okay. First of all, I think it's a brilliant idea to get this Fermi surface maps by doing Fourier transform. Maybe the first question, which we can discuss it later, maybe. So here, this DIDV that you are getting, I mean, do you think it's reliable for a multi-band systems? Because when you do STM, you are getting the contribution from all the electrons together. So, but the kind of systems that you have, there are several bands that contribute to the Fermi surface. So how do you deal with that?
Okay. So let me tell you. So basically what you see here, so first off, let me answer one, let me tell you one thing. So for example, if you have a many band in your Fermi, in QPI, you may see less amount of band scattering. May not be the all band will involve in the scattering and you will see in the experiment. It depends upon the type of scatterer you choose. Maybe, for example, here the defect scatter much stronger to few of the bands, but step edge scatter some other bands stronger. So basically, in here we didn't resolve all the band scattering here, but in the other scatterer you can choose other scatterer and you can find there whether they are susceptible, with the scattering or not. But yeah.
But how do you make that choice?
Yeah, we don't have choice. It is purely.
The second thing is that, I mean, the Fermi arc that you are talking about, I feel it's a bit too ambitious way of saying. Of course, you have got a high-tech publication. I don't want to complain about it, but you know the Fermi arcs. So I mean, do you really see the like in while nodes that you have the Fermi arc? They are connecting to two different type of Dirac nodes. While nodes. So
yes,
if you do the Fourier transform from the DIDV at different energies, so you should be able to also construct the band structure. Is that so?
Yeah. So actually, I didn't show you the other data because of the time constraint. So actually, now let me tell you one thing that then probably maybe it will be easy to convince you the data. So here what we do is basically we have a steppage and we made a linear, so it's a line cut measurement, like along this direction, we measure the density of state measure.
Yeah.
So now this is the result, but I have to go back. Oh, I'm sorry. So basically, so now this is the di over dg along this length. And this is the spatterer, the steppage is the scatter. And we generally choose perpendicular to it. And now when we have this, the atomic resolution picture, then you can assign the in the crystal structure in which direction this state propagates. And perpendicular to that, the QPI features, this interference pattern will be much stronger. So basically all the information that we get basically along gamma to m direction, and which is basically, it is 49 degree, that means 4 degree up to gamma to m. So basically this is the QPI along that direction. Now what we do, we see the ellipse band, this ellipse band scattering at the center. Now let me go to the, sorry, yeah. Now let me go to here. So now if you look closely here, then you will see two kind of oscillation. This in this di/dt map. Now, at this moment, if you just compare with this topography, then immediately you can isolate that one contribution is come from arsenic atoms and other contribution comes from tantalum atoms. Now, since we know this length scale and also we know this atomic result structure, this measurement, then you can just divide it to so one contribution you can take from tantalum side, one contribution you can take from arsenic side. And when you do it, then arsenic, because arsenic dangling bond is basically is a trivial band, but actually this topological state, that wild fermion that comes from the tantalum band. And if you know, so this is basically the scattering actually that happens. So basically, if you know this, if you see this scattering, and if you just take it here, and up to this point, we have this data. Now, if you just extrapolate it and come to Q equal to 0, it exactly see this energy state of the wild node in the bulk. So see, we are measuring on the surface, and surface Fermi arc know the energy position of its wild and the bulk wild node, which decided the bulk. So basically, all this topological material, most of them shows this the bulk surface correspondence or bulk boundary correspondence. And so basically, those states at the surface due to its bulk property. So in this experiment, we exactly see this correspondence. That's why
you are suppressing this arsenic contribution is just by removing the corresponding oscillations, or?
Yeah. So for example, how we measure. So you see along this line, we go pixel by pixel, and we can fix the length of the pixels. So generally in this measurement, I remember it is 0.5 angstrom apart measurement. So that means it is very smaller than a bond length. So that's why it is a very accurate, I mean, very accurately you can go on atom, off atom, or you can just choose those contribution, which is with those pixels from these atoms, this arsenic atom, and those pixels near this tantalum atom. And just you distribute and just you don't, divide it, and it immediately see all the bands that you see. For example, this is the whole QPI from the as it is measurement. Now, when we go to this, separate this to subsection, and this V-shaped band also come, which basically is coming from the arsenic band. And also, this is a calculation, and with this experiment, the calculation exactly matches, and the position of the wild nodes exactly matches. So, in 3 ways we show in this experiment, in 3 ways we show this the Fermi-arc existence on this surface. Not only I show only one today, but yeah.
Okay. Thank you. Yeah. Thanks.
Okay, very nice talk, Rajiv.
Oh, sorry. Okay, sorry, I was muted.
Yeah, I saw your mic was muted. So.
Yeah, sorry. Quick last question by Professor.
Yeah, I have a small question that the elliptic band that you showed, I have not seen that band from ARPES. What is the origin of that band?
So to this one, in this one,
the elliptic band around gamma.
Okay. So this elliptic band around gamma is basically, so this is not a RPS. Actually, RPS, you will see exactly this Fermi surface as I'm showing you here. So at the gamma, you will not see this one.
So but you see that?
So yeah, so basically what you see, this is a Q vector. So basically you get the difference between two bands. So for example, if there is a scattering take place within this ellipse band, this blue band, then basically Q vector is nearly very small amount. So it is very nearly to 0. So that's why this peak comes at this center.
Okay, but so, then in RPS we should see it here, right?
In RPS you should see this Fermi surface, exact calculated Fermi surface.
What about the elliptic band on the side that you have drawn, which is scattering? That should be seen in RPS also.
Scattering is difficult actually, because it exactly. I mean, you can see all the you can see this band and the Fermi arc as well. So in RPS, this material has been experiment has been conducted on this material, and they show it, and it exactly similar to this calculated one. Actually, I forgot to include it. I should include it, the RPS measurement as well.
Okay.
Okay, thank you.
So, Atin, may I ask for a small clarification?
Yeah,
Yes,
yeah,
please.
maybe quickly, yeah.
Yeah, so Kaluda asked about the scattering for this kind of experiment for multiband systems. At some point, you mentioned that the scattering for different bands, I mean, the impurities can scatter the electrons from the different bands in a selective way, right?
Right. This is what our experience in this material.
I know. How do we understand that?
So I am not. This is very difficult actually, because these are the random. We don't know exactly the structure of the potential, the potential of the scatterer. So sometimes the different scatterer.
Whatever it is, why should it be different for different? Means why should it not scatter some of the bands at all? That's what I was wondering actually.
So actually, I mean, there are many cases where, most of the band doesn't scatter. This is, and then the experiment gets failed. So basically it is, and also another aspect we should also think about, that it only happens, this scattering process only happens near Fermi energy. If you go beyond very low in energy or high in energy, and then, so far what I have seen is about all the QPI is about around ±1 EG or something. So this is one thing, but other thing is completely depends upon I think the structure of the potential, scattering potential, which is it is very, actually at this moment we don't know how to probe them with STM or other techniques, but I think it will depend upon that.
So these are elastic scattering, right? So
these are elastic scattering.
So whenever Laue condition is satisfied, there should be scattering for all bands, no?
Yeah, but that the scattering also, probably it's scattered, but you have to detect with your tools. Okay. But the detection also goes with this some probability value. So I don't know.
Okay.
So in that, all the thing will come to the picture.
Okay. Thank you, Rajiv.
Okay.
Thanks.
I think you can discuss later, but there was very nice talk by Rajiv. So thank you, Rajiv, for this, and I think I hand over to the organizers.
Okay, thanks, Atin. Thanks for sharing the session. Also thankful to all the speakers who are giving wonderful talks in this session. So now I think we have the lunch break. We will reconvene at 3:30. Actually, there is no poster session, but still, there are no live poster session today. But still, you can go to conference website, and there already you can see the e-posters. If you are interested in, you can go to, like yesterday there were 2 posters, and those posters are available, and you can go through them. Okay, then let's meet again at 3:30. IST.
Hi, Kaluda. So you arrived. You successfully arrived, Kaluda. This is Gautam. This is Gautam, Kaluda.
Yeah, I wanted to see you here, but
you said that you would go physically, but you actually made it, huh? Oh, acha, okay. Okay. So you said that you would go, but you actually. Okay. Bye.
আমি ভেবেছিলাম তোমাদের সবার সঙ্গে দেখা হবে, তাই একবার এসে গেলাম। ভালো আছো তো?
হ্যাঁ।